Hello, everyone. Um, Welcome to our Industrial Health Seminar Series. My name is Serena, and I am the CE Director for the Southwest Center of Occupational Environmental Health. This is my first industrial health seminar, so I'm very excited to be a part of this and to meet all of you and to meet all our great speakers. We'll just go over a few housekeeping items. Best practices for a successful WebEx session. If you are using a VPN connection, consider not using it. Often this feature can limit the bandwidth available to WebEx and cause connection issues. If you do have a poor connection, try changing your audio. If you use call using computer, sometimes it slows down the connection. So to avoid this, try doing the call me or I will call in option if you have any trouble hearing during any time of the session. All attendees will be muted for the session. So how do we communicate? Use the chat box to communicate help needed. Use the Q&A box for questions on presentation content. Select all participants in the drop-down menu so the moderator and presenter can view questions. And we will be answering questions at the end of each presentation. Video cameras are only being used by the panelists today to aid in having a strong connection. Please close all other applications that you're not using at this point to make it for a smoother connection. This event is being recorded. Our agenda today, we have speaker Doug Rush, who will be talking about occupational exposure assessment and how to implement the ARECC process in the workplace. We have David E. Downs, who will be going over a review of development and current state of qualitative exposure assessment approaches. And we have Bruce Nauman, who will be talking about health-based exposure limits, basic methods, and new approaches. And then we will have a wrap-up roundtable and evaluations. Thank you to the agenda producers, guest speakers, and all our participants. And many, many, many thanks to Jan Cohen for gathering this great group of speakers today and for putting this presentation together. A little bit about the Southwest Center for the Occupational and Environmental Health. We have training programs, outreach, and continuing education and research and practice. Our areas of interest are industrial hygiene, occupational environmental medicine residency, occupational epidemiology, and total worker health. Some of our upcoming events this evening at 7 p.m. We have our Occupational Medicine Journal Club, where one of our residents will be presenting on published scientific research. Tomorrow, we have our EOHS Research Seminar Series, which is free and open to the public. And next month, we have our big Environmental Health and Safety Academy Part 2. If you did not attend Part 1, that is fine. Part 2 is available to everyone else. Our EHS Academy is for safety professionals, how to recognize workplace hazards and how to address them, specifically for those who work in research and academic settings. If you would like to get more information on our programs, you can visit us at SWCOEH.org. And we are on social media, on Facebook, on Twitter, at SWCOEH, and also on LinkedIn as well. So we will have our first presenter, Doug Rush. Doug is a hands-on, results-driven health safety professional service leader with more than 40 years of leadership and senior operations and management. Doug has founded and owned 3 full-service HSE consulting firms and a staff of up to 40 full-time professionals. Doug's experience has been focused in engineering entities and Fortune 1000 companies positioned locally and internationally. So his presentation today will be on occupational exposures assessment, how to implement the ARECC process in the workplace. Thank you, Doug Rush.
Hey, thank you. I appreciate it. I hope you guys can see this. What are you seeing? Can somebody answer? Is it just the full screen of the slide, or are you seeing my notes? Okay, I guess that means we're seeing
We
full.
see both you and the slides.
Oh, great, great, good. Okay, so anyway, hey, thanks for this introduction, getting me started here. I'm always honored to speak with people, my peers especially, and it's always just a little bit intimidating to speak to my peers because you just never know when they're going to catch you in a lie. So if you catch me in a lie, just let me know. No, I'm not lying to you about anything, but what I'm going to do is just share with you a subject that is a passion of mine, has been a passion of mine since I entered the industrial hygiene field way back in 1979. I know recently we've invented, it seems to me like recently we've invented this word ARECC process, but most people who have been in industrial hygiene for a while no, it's the same old thing that we've done. We've just put a different label on it. I think the ARECC process has a real good way of kind of spelling out for people who are particularly new to the field the process on how we get from one thing to another. My goal today is just to share some information from the School of Hard Knocks, many books, things that I've learned throughout my career, and not only from books and stuff like that, but from you, my peers. Exposure assessment, as I've mentioned before, is a passion of mine. I never stop learning. I came to H-Town, or Houston, for those of you who are not in Houston, and I think most everybody here is in the Houston region, in 2002. The first thing I learned when I got here was there's a lot of really smart people here. So as I go through this presentation, if you guys see something that you want to talk to me about later, man, jot down a note and let's talk about it sometime in the future. Because I'm not gonna say that I've got it all correct. One thing I've learned too, particularly about working with my peers and speaking with my peers, is that forming the network that we all have here is so valuable. Back in 2014, I'll never forget, there was 4 people were killed in a chemical accident here in Houston. The CSB was responding, and they were going, it was a large plant. Some of you who live in Houston know what I'm talking about. And the CSB was going into the plant. They had no hygienist. They were a little afraid to go in there on their own, so they gave me a call. Asked me to show up, and I spent quite a while there afterwards working with them to help make sure that their health and safety was not in jeopardy. And what I learned about that is the value of having peers and knowing them was on my way out there, I had no idea what was going on at this plant. And I just started calling my friends, people like you, and just asking, what do you know about this plant? What's going on? Yada, yada, yada. By the time I got there, I was able to present a sound strategy on how to proceed to the next step. And I credit that, my friends and peers and that kind of thing, to managing to get through that issue safely and to figure out what was going on. That particular company, and it's a large company, and some of us in this room are associated with large companies, and sometimes we get into that mindset of large companies can do no wrong. Well, this particular company, and I'm not even going to mention their name, if you know who it is, then you know. They were on the naughty list for severe violators, and they're one of the noted companies in the country for just having outstanding everything. So just because you're in a big company may not mean that you got the best program out there, and I think that's the value of going through things like this. Okay, so I think I've switched the slide to the next slide here, and I think many of you in here can recognize this picture. They say that a picture says 1,000 words, but what do we see here? You know, I think most everybody by now, I mean, we've seen this object in our skies for about, what, couple, 3 weeks now. What do we really know about it? I put this picture up here just to kind of show you that sometimes a picture and sometimes the things that we write down, we don't get the entire message down very well. Like this particular thing, this is the balloon that's been flying or flew over America for quite a while. And we still don't know a whole lot about it. It flew over my farm in Missouri. I don't know why. Maybe they were trying to see how we are operating tractors. I don't know. Maybe they're trying to see military bases. We just don't know what's going on here. So I put this picture on here just to show you that a picture doesn't necessarily say 1,000 words, as well as reports and things we write that don't necessarily say 1,000 words, which is what is very, very important whenever we're dealing with the ARECC process. It's a process that can used with other tools that we have in the industrial hygiene field. It's a good process that we have spelled out to be able to help other professionals in our career field or people outside of our career field understand what's going on. So we're going to talk a little bit about that. Here's another picture I wanted to show up here. You see on here, you see a nice gentleman here with looks like an air sample pump on him. Looks like he might have a welding helmet on, some safety glasses. Just looking at that picture, we just don't know what's going on here. We don't know exactly what's being sampled for. We don't know how long he's being sampled. We don't know why he's being sampled. We don't even know where exactly he's working in this facility. We don't know a whole lot of things. So the ARECC process helps us to identify and write down those things that are important to know about a process just like that. Here's another picture of a guy who looks like he's got on a space age type of a helmet. This is what do we know here? The same thing. We see on this guy, he's got a noise dosimeter on, but we don't know if he's exposed to high noise levels for an hour a day. We don't know if he's exposed to low noise levels. We don't know where he's at. We don't know anything by looking at this picture. I just trying to put a visual in your mind to show you that the writing we do about things that we do in our career field is so important. And just think about it as a picture. When you put down a written document somewhere that documents what it is that we're doing, you got to think back. What do people not know about that? I do a lot of expert witness work, and one of the things I find out is that much of the documentation that we do out there is not very good, just to tell you the truth. Some of it's very good. This is a Dwyer manometer, which many of you have seen. It's a picture. It tells us something here. It's the same thing. Why is this detail important? And the reason I ask that question is because this is on a particular paint booth. Do we need, whenever we do an air sample out there in the workplace, do we need to know this kind of information so that we can match it up to what was actually sampled, where it was sampled, was it in a paint booth, that kind of thing. We need to know all that kind of stuff. I've been very blessed in my career field in that I started out as an industrial hygienist in the United States Air Force. And there we had any of you who have been in the Air Force know exactly what I'm talking about. We had a great process for documenting industrial hygiene observations. And so I've been documenting stuff like this for a long, long time. But I do know, as being an expert witness, many times this is what I get from a field. This is a particular, it's probably kind of hard to see. I hope you can see it better than I hope you can see it. This is a picture of a process in a plant that I was testifying in. This is a plant that had 2 CIHs assigned to the plant. I was working for them, helping to defend them in a occupational exposure case And one of these IHs had been there at the plant for 20 plus years, long, long time. The other one had only been there, maybe a year. But this is the kind of documentation that they were producing in the task that I was asking for information on, what they had sampled for in that place. And if you look at this, we can see a little bit of it. We know maybe this is compounding. We can sort of take away from this that this might be a process where we were sampling on a person. It might be an area sample. We don't know how long of a sample it was. We don't know if it was a 10-minute sample, 15-minute, 1 hour, a whole shift. We don't know if there was exposure before or after. But in that particular case, and this is one large company out there, they were hanging their hat on this data. This individual who happened to be a contractor who had turned out being underneath the OSHA rules, being classified as some sort of an employee, had suffered a significant damages to parts of his body. The company, when I was trying to get information on it and asking them to explain this information to me, they just couldn't do it. So what I'm telling you is just because you have qualified people in your plant may not mean that they are actually documenting things in the appropriate way. So the AREC process kind of helps us to do that. So what is the ARECC process? Many of us in here have heard that before. Some of us have not. Place I found it on is the AIHA, and I think that they were the ones who come up with the word. I don't know. Some of you in here might know. I love it. I love the word. It's very nice, particularly in a courtroom whenever I'm testifying on your behalf or someone's behalf who's asked me to come in and help them defend against something. It's an easy way for me in the courtroom to just tell them. It's a 5-step process that we go through. First step is anticipation, then recognition, evaluation, and then controlling of the hazard and confirmation. So you can just kind of walk through all those pieces in a courtroom, and it helps you and me, and I assume most everybody in this meeting is an industrial hygiene type people. It helps us understand and help the courtroom understand what we actually do, because as you know, or as I know, or as I think I know, for many, many years, explaining what we do to the general public is extremely hard. This is a nice, easy way to do it. One of the things I want to point out on this thing is the last sentence on here. It says, this thing is used by hygienists and safety professionals to talk about workplace stresses and to help identify and those kind of things. And the last few words on here says, are among citizens of the community. So this ARECC process is something that we can use for work in the community. Is that important? Well, of course it is. We've all went through the pandemic, and we all know that our work started becoming very important for the community. I participate, as many of you do, probably on some of the AIHA chat boards. And one of the things I noticed whenever we started that pandemic, I saw some people, some hygiene people getting on the chat board and going, what's this COVID thing got to do with us? And for me, I thought, man, that's just a crazy question. But because I've been dealing with exposures to the community for many, many years, as I know many of you have here. But literally, the process we do is very, very useful in exposures in the public. Some of the stressors that are associated with the ARECC process is biological, spiders, snakes, powder, who knows what is out there, plants, those kinds of things that can affect us. Chemicals, physical, ergonomic, and yes, psychosocial factors, workplace violence. This process can be used very easily in that whole part of the game. This is a diagram that was put on the AIHA website, which I really liked. It some of you in this room are in this seminar right now recognizes this very easily, and if you've heard of if you're working with the ISO programs or maybe any other management type of a program, you've heard about this process before, and this is part of the Plan, Do, Check, Act, PDCA management. And that's all the ARECC process is. It's part of the Plan, Do, Check, Act. And what we have is a continuous type of a circular pattern at the top where we anticipate and recognize hazards. Then we evaluate those exposures, we control them, and then we start back over. Through this process, we conduct hazard assessments and inform people, do our risk characterization, and then come out with an outstanding risk management program. If you got a program other than what the one that I showed you earlier was like, where you just take samples, you don't know why you're sampling, or maybe you do, but you don't put down enough information so that when the guy or the gal behind you comes in to replace you because one day you don't show up for work, either you retired or something else, that person can take the work that you've been doing for 10 or 15 or 20 or whatever years and just go from that point on. They don't have to reinvent the wheel. So let's talk a little bit about the steps of the ARECC process. Anticipation. This is just the step where we, everyone here is going to go, duh, I know that. This is just where we identify the hazards. How do we do that? You know, how do we anticipate hazards in the workplace? Well, some of the ways that we do it is put permits in place in our plants. We have a permit process that is put into place where people have to come to us and ask us, you know, how can we do this safely? Or they have to tell us their plan for doing a process safely. Maybe they're going to weld inside of a tank that has contained some sort of a petroleum product. So they're going to tell us exactly how they're going to do it, what precautions that they're going to use to make that happen. So this is all part of the anticipation part. It can happen from chemical inventories. One of the things that many of you probably have in your workplace is a process set up in the supply area, or the place where your supplies come in to the plant, that if somebody's going to buy a chemical, that chemical has to be put on a form and sent through the safety and health department, where you do an evaluation to ask, what are you doing with this chemical? What's going on here? How are you going to use it? What are you going to do to make it safe? This is all part of the anticipation of it. 5-year plans are important, where a company has a 5-year plan and they're talking about their growth. This is where people like you and me get involved, and we start anticipating some of the issues that may be going on as facilities start being built out to deal with these things. Do we need ventilation systems in there? Or, as I've seen, and let me tell you, 40 years in my career, what I see more often than not is the health and safety people are not involved in this process. Building out something until suddenly it shows up on their door. If that sounds like you or your organization on their doorstep, if that sounds like you and your organization, you probably need to talk to your management team about that. How to plug you in sooner. And for most of us, or a lot of us, I've worked in these big organizations. I've managed some very large programs in the world, like Learjet, the United States Air Force. I've managed some very large programs at International in depth. And what I know about that is our hands are full whenever we are a company asset. So one of the things I've learned as a result of that, maybe I cannot do it all by myself. And maybe what I need to do is to identify some resources out there that can help me. So if we have a process that's going along and people are putting in a plan for 5 years of doing some new process, I can get them involved in it at some point along the way to help me to identify what it is that we need to do in the next steps. Particularly when you're building out a plant, that's the best thing to do because money should be available to make stuff like that happen. Recognition, the same thing. So this is the next step. So, and part of these things are kind of associated with the other one. But so now we know that we're going to use chemical X, or we're going to use a process that's new to us. We're going to do some sort of welding. We're going to do whatever. So now we go to the try to recognize what the hazards are. Where is it going to be done? We look at everything from safety data sheets. If it's a process that's already going on, maybe we can get a direct reading instrument out there and use a sample tube, or whatever it is that we need to do. We can use it past, we can look at data that other professionals have gathered and shared with us through some of the sources that we have available via the internet, our libraries, etc., to try and see what some of the other exposures have been. This is one very important part of what I do whenever I have an exposure and I'm put into the testifying mode. Many times I go into a chemical an exposure in a company, and I find out that, well, there is no data in the company. That's worse than just having a list of chemicals that we tested for and we don't have any other data with. So a lot of times what I can do, and you can do too, and some of you in this room do it already, is go look up what other people's experience has been. For instance, I did some expert testimony on some people here recently that were exposed in the 1960s to asbestos. They were pipe fitters. So I went to some databases and identified various sorts of sampling that may have been done or not done to help identify what sort of exposure might have occurred to this particular pipe fitter. And you can use that to kind of rebuild the scenario that's going on out there. So there's a lot of information out there. And evaluation, this is the one that lots of us do all the time. Many times the A and the R part of this thing, we just do it intuitively. I mean, we've been in this thing a long time. A lot of times we don't document what we've done, but many times we go straight to the evaluation. Many times when I'm asked to come out to a plant, a lot of times this is what I end up having to do, is take what they've already got and go straight to an evaluation. But we're trying to identify the extent of the hazard. What is the level of exposure? What's the likelihood of harm? And what's the consequences of exposure out there? And we do that many ways, everything from using some of the tools that we've already talked about to direct reading instruments to sampling processes and things that we want to send into a laboratory to get a little bit more information on. So the evaluation is one thing that most of us in here are probably really good at. However, I say that when I was in the United States Air Force, and I know this is true for many of our workplaces now today, is a lot of times especially the hygienist, a lot of times is put into a position where he or she has so much to do that they really can't do a whole lot of the sampling. So what do we do on an evaluation part? I'm going to show you in a little bit. Maybe sometimes we do some modeling. But again, maybe we call somebody in to help us out. I've seen way too many times where I go into a workplace and I'm dealing with a health safety person, environmental person, and they have got no idea what's going on in the workplace. and they've been there for years. And in fact, I can even call sometimes the people at the plant and ask for the person. And sometimes, and I hope this is not happening in your plant, people go, who? Who are you looking for? I don't know him, or I don't know her. I can tell you that happens a lot. And if that's in your workplace, you probably need some help. Either you need more staff, or you need some outside help, or you just need to get out there and look around and see what's going on. The next step here is control. This is such an important thing, and usually this is way beyond most of us out there. The control step involves implementing processes in the workplace, including industrial ventilation. Maybe you got an open top tank where you're putting some balls on top of it to control evaporation. Just all sorts of control measures that are out there. It could be administrative controls where you are swapping people in and out of a place to limit the exposure. It could even be PPE. So this step is pretty important in the process on the control. So you can kind of see as we've gone through here the steps in the process. So now we want to confirm. I cannot tell you how important this particular process is, the confirmation. This step just involves monitoring and evaluating what's going on in there, the effectiveness of your control measures. How many of us have ventilation systems out there that we know they're there, we don't really understand what they're doing or how well they're working. We don't really know if there's a preventive maintenance program associated with some of the things that we're using to control exposures out there. That goes for a lot of us, not all of us. Some of us in here are going, man, Doug, I got this. This is no big deal in my operation. We deal with that. And if that's you, man, be thankful. I can tell you, I don't want to put a hard number on it, but the overwhelming majority of the workplaces out there with high-end and low-end professionals have no idea what's going on out there. And then as a result, they can't even confirm what's going on. I can tell you that having been through so many work sites, sometimes I'd go out there and help them identify these issues, give them some of the document that I'm going to show you here toward the end of this thing, and they don't. And I can spend time with them explaining it and what they need to do and the next steps. And once I walk out of there, it's done, you know. Incident reports are part of our confirmation process. So we think we got something controlled, but we're having incidents. What kind of incidents are we, investigations are we doing out there? It's all important. As I mentioned, this is part of a PDC plan, do, check, act process. It's a continuous process where you just keep doing it over and over. I'm going to show you a document here at the end, which is found in some of our standard industrial hygiene references out there that helps put this entire process together, and it helps you to reinforce it. It provides a system where you can follow up on these things easily, at least once every X often, whatever it is that you've decided as a company that you want to follow up on. Here's an interesting picture that I took just off of the internet just in the last few days. Some of you in here probably know what this is. This is in Ohio. This is that train wreck that happened here recently. We've all seen the information on the TV and seen the fear that's going on out there. We've all heard about dogs dying, animals dying, people with issues associated with their respiratory system, their eyes. People don't understand what's happening out there, the whole 9 yards. What my question is can the ARECC process be used here? Yeah. No, answering right now probably ain't the easiest way to do this, but at the end of this, if we have time, you know, let's talk about some of these things. But yes, it can be. I mean, this is all part of PSM, process safety management. Train system going through a town. I was involved in a big train wreck up in Canada several years ago, I think 2013. Could that explosion have been anticipated? Could we have recognized what the issues were up front? Could we have done evaluations before any of this happened? Yes, we can. It's all part of the PSM process. And now look what's happened. This company, I don't know who it is, which railroad company it is. I think it was Norfolk Southern, or I can't remember. But they're in the middle of something that could potentially run these people out of business over time. I mean, the PR on this thing is awful. But the ARECC process is something that we very easily can put into the PSM programs. And that's basically what the PSM program is all about. The same thing. You know, I mentioned earlier on about can or should the ARCC process be used in a pandemic? You know, on the chat page on the AIHA that I dealt with or read or talked a little bit about earlier, you know, there's industrial hygienists that think, no, you know, I mean, I think most of us now know we could, but initially, whenever this occurred, I saw lots of comments that says, this is out of our bailiwick. And I'm here to tell you it's not. And it's all part of the ARCC process. This was some sort of an emergency that came out. Well, so what happened here? And this is kind of important, you know, we started implementing in the nation, as a nation, we started implementing processes of wearing a mask or no mask. There was a lot of debate about that, whether you agree with it or not. I think most of us as hygienists understand the benefit or no benefit associated with this particular process. And I can tell you, based upon my experience, and I bet you can tell me the same thing, is that many of us right here in this seminar, probably half of us think that the mask was a very useful thing to avoid exposure. And then the other half don't. And now we're starting to even see on the news second guessing about what happened there. So was the ARCC process used here? No. Probably it started out that way. But politics got involved. And I think from our standpoint, what we do with the level of management that we're involved in, we just always need to understand the influence of politics on things. So we need to understand that Chicken Little phenomenon will occur. What's going on in Ohio right now? You know, there's a little Chicken Little phenomenon. The sky is falling out there right now. People are scared. People don't know. The same thing happened in the pandemic. People are wanting to do something. They don't understand what to do. And part of a PSM process, which is part of the ARECC process, helps us in advance to put together procedures that can help to avoid this sort of thing, to where we understand the public a little bit better, and can not only that, we understand our politicians a little bit better, and we can learn processes to communicate easier with our process, with our politicians that are out there that are typically the ones who are, at least since the pandemic, been regarded as the experts when it comes to exposures like this, which we all know is just not true. Politician doesn't know that kind of thing. So we just need to, in this process, understand what we're dealing with so that we can talk to people. Same thing goes with carcinogens. I cannot tell you how many times I've been in a workplace where someone thinks if I'm exposed to one molecule of a particular chemical, I'm going to get whatever it says I'm going to get. It's just not true. So we have to develop in advance processes associated with that. So one of the nice things about being a member of the AIHA is they've got a really good website there that kind of directs us to models. Models that can help us to identify chemical exposures and what they may or may not be able to do to us. Everything from noise to chemical substances, the whole 9 yards. Some of these models are extremely complex, and some of them can be interpreted wrong. I know I'm a victim of that. I mean, I've used at least one model on here that I used incorrectly. I got it right before it hurt anyone, but I think we have these models, and a lot of the reasons why we use these models is, number one, to recognize an exposure or a hazard that we cannot go back and reproduce, or to predict what may be going on prior to something happening out there, or they substitute for doing exposure sampling in the workplace. Those of us in this room that do a lot of exposure sampling out there, the cost and the analysis of a sample is very expensive. Sometimes a metal sample on a welder could cost anywhere from $100 to $200 per sample, and that's not counting the cost of the labor. And if the person who's doing the work has to spend some time to sit there and interpret it and write it down in a format for which it can be understood, a year later or even tomorrow, it just takes a lot of time. So sometimes you can do a model, and these models will help us understand in advance or after the fact what has happened. There's a lot of models. I want to encourage everyone here, if you have not looked at it, the AIHA now has a bunch of models. And then there's tons of models out there, which we're going to talk about right here. Chat. This is a great tool that's out there. I'm becoming addicted to it. I love being able to go to this model on chat. It's just if you're not used to, if you've not done it before, get on it, take a look at it. You can ask it a question, and man, it'll spit all kinds of information out at you. But you got to understand what its limitations are, at least for right now. And I'm sure they're getting better as time goes on. But if you put garbage into a model, you're going to get garbage out. And so that's what I want to show you here. Like, for instance, if you go into the chat right now, it's not going to, it's a little different. If you ask this particular question, it's not going to give you the answer that I'm fixing to tell you. But if you put in there, who's the greatest country in the world? Well, guess what? The answer to that is not that simple, right? And if there's only been one country that's been programmed into this chat model, like Russia, and you go, who's the greatest country in the world? The model's going to spit out Russia is the greatest country in the world. I think that there's like 500 or 600 countries in the world. So you have to put all the data in there, and then probably this model, if it's operating correctly, is not going to be able to tell you anyway which one's the greatest country in the world. But this is a great model out there to help us identify some of the things that we need to identify. Like maybe you need to know how much ozone is produced by an ozone generator. You could put that into a question in there, and it can at least get you started. One of the things I think we have to recognize as being industrial hygienists and professionals in here is that other people are using this model to ask the same questions, like how much ozone is going to hurt me. And they're not going to understand it. So the information they get out might be wrong, and they're just going to run with it. Same thing that might be going on in Ohio right now. Some of these chat models might be being asked, and that could be what's creating some of the tension that's going on out there. So just understand that a chat box, or these open AIs, which are phenomenal out there, you just have to understand the limitations associated with it. And that's not just a chat. That's all the models that we use. And then there's some other models I thought I'd just throw up here. I know most of you guys and gals in here have experience with some of this stuff, but this is part of the ARECC process. Some of these rules of 10, vapor hazard ratios. If you're not familiar with these things, particulate hazard ratio, these tools can help you identify, I want to say identify, evaluate, control, which is what we always used to use, but they can help you to anticipate, recognize, evaluate, control, and confirm exposures that you've got out there. So you need to deal with something that there's a potential exposure in the workplace. It's a new exposure. You can work out some vapor hazard ratios and get an idea as to, well, do I have this problem? Or it's an existing process. You can use some of these rules that are in our IH resources out there, which if you've been in the field a long time, you've probably seen these things. You may not use them anymore, but I'm just throwing them up here so that you can be aware of them. One of the things about industrial hygiene, which I like to talk about, and I know everybody, I'm talking to the choir here. And I know that. I know most of you guys in here know a whole lot more about this process than I do, and I do not even discount that. So I'm just sharing with you some of the stuff that I know, and I'm putting some simple stuff up here right now, just in case that there are some people in this room that don't. What is industrial hygiene? Well, I like the first line of this, that science and art devoted to the anticipation, recognition, evaluation, control. I think it's important to understand that what we do is an art. Many times I talk with people, safety and health people, not so much hygienists. I think most hygienists understand this, but I may be wrong. Many of them don't. They don't understand that a lot of times this is an art. The process that I'm going to show you here at the end of documenting some of this information, a lot of it's an art. It's the use of professional opinion based upon your past experience, especially whenever you're doing an entire workplace. Like I've done a refinery before. I've done several refineries actually where they had no data at all. And you go into the refinery and they may have a poor IH out there who's just been working his butt off and for all these years, and he still hasn't got a handle on stuff because he keeps getting involved with all these other little projects every day, which that happens to us. If you work for a big company, you know what I'm talking about. So one of the biggest parts of the job we have to do, in addition to all the tools that we have there, is to employ that art as part of the identification or the anticipation and recognition of issues out there. And that art is the same thing that a doctor does whenever you go in there and go, Doc, I got this itch. You know, so the doc asks you a few questions, runs a few tests. Maybe he doesn't run a few tests. Maybe she tells you, okay, we're going to take this or whatever. But they just run it through a process over time. We are very much subject to that because of our science is huge. It's huge. And I know I'm talking to the choir and I've said that over and over here, but just recognize that what we do, I have sent industrial hygienists out on I'll never forget sending out an industrial hygienist, a senior hygienist who I trusted and I trained over several years. I sent her out to do this exposure evaluation and document it as I'm going to describe. And she hesitated at the art part of this. She didn't understand how to do the professional opinion part of this thing. It's a very difficult concept for most people who are engineers and scientists to understand sometimes that a big part of our field is an art. So we're dealing with and supervising people that are like that. We just have to understand that and meet them where they are and talk to them about that and get them comfortable with it. I don't know about you, but the first time I was exposed to the art part of this thing, I was uncomfortable with it too. So it's just something that we all go through. We need to understand things about the dose. Um, Everyone's seen this before. Dose does make the poison. Even, I've heard that I think about a spoonful of water, you can drown in it if it's breathed into your lungs. So, dose and how you're exposed to something in the workplace makes a big difference. Part of the ARECC process evaluates that. And all chemicals have, you know, toxicity, but it may just be not necessarily the type of chemical. It could be how it's being exposed. You're being exposed to it. All the difference between a medicine and something that's poisonous is how much of it you're given. Everything up through cyanide. I mean, we give, if I'm not mistaken, I think we give warfarin to people to thin their blood. Those of you who are familiar with warfarin, you know that's a rat killer, right? So we thin their blood a whole lot to kill them. So it's just a matter of how much of it we give them. These are some very simple things that go along with the ARECC process. These are typically the four routes of exposure, which I'm not going to go over this, but I think so many times, many of us forget the importance of the last three. We focus on inhalation. And the last three, skin contact, what we can absorb in our skin is just as important, or maybe even more important than the others. I'll never forget, many years ago, I had a jet mechanic that was working on fuel cells, and his benzene levels were consistently coming up high. I did all sorts of air sampling, etc., did lots of calculations, all sorts of things, and his exposure to benzene while he was working on that jet was not an issue. And then one day he came in my office and we're talking some more about what was going on, and I noticed that his shirt pocket was wet. And I go, "Why is your shirt pocket wet?" And he goes, "Oh, I've been carrying this leaking lighter around for a long time. It belonged to my dad." Well, those of us who know, that leaking lighter has fuel in it. Some of it was benzene. I took it away from him. Didn't take it away from him. I told him, don't do that anymore. His benzene levels went down. So sometimes we just have to understand that these other things are important and we cannot overlook the importance of these things. This is simple. There are many different types of exposure limits out there. Many of the plants I work with want to stick with the OSHA permissible exposure limits. Some of you out here want to stick with some of these other limits, ACGIH, NIOSH, etc. The limits are different. I know I'm talking to the choir again here. I just want to throw this up out here. If your plant or where you work has not identified what levels you want to be working with, you need to do that and then stick with it as you're doing your exposure assessments. Many times I've seen people pick like ACGIH levels for the ones that we're going to use. And then we go out there and the exposures are high. So what they do now, oh, well, we're just going to comply with the OSHA limits. Well, that's fine. If you're dealing with OSHA, you can fool them. There's no doubt about it. But in a courtroom, you're not going to be able to hide behind that as easily as you can with OSHA. I just throw that up there just so you recognize, and you guys know these terms here: action levels, ceiling limits, sampling and analytical errors. We know how they impact what it is that we do. Ceiling limits, I don't know about you, I'm gonna tell on myself here, but I think I was in the career field for a long time, probably 10 plus years, and thought a ceiling limit, was a 15-minute limit. And then I read the NIOSH book, and I'm going, oh, well, a ceiling limit can be defined differently. So we just need to know what it is that we're dealing with and how it is that we're dealing with them. Exposure assessments. I cannot tell you how many workplaces I walk into that they have no idea what the exposures are in a workplace, even plants that have been around for years and years and years. But employers are required to do that. So do an exposure assessment, particularly for the respiratory hazards. So how do you do that? Here's what I see. A lot of the times I go out there and people go, oh, they're not exposed. And I go, how do you know? Well, that's the answer. They don't know. They don't know, or they say mumble something. Like the hygienist who did all the sampling that I showed you earlier, he goes, they're not exposed to this particular item. And I go, so how do you know? He goes, oh, I got data. And then he produces the data. What did he know? So that's without doing the exposure assessment and a process that I'm going to show you here in just a couple of minutes. You just don't know. You don't know. So you have to do these things. This is the typical. This came out in 1977, I believe it was. There's a NIOSH book out there, the sampling book. Many of us in here might have seen this before. This is kind of the predecessor of the things that we use today. It's really nice. It's a nice little diagram that NIOSH put out. You can find this online. It's a free book. I want to tell you, concerning industrial hygiene reference tools, the information that's in this book has really not changed. We might have updated it and got it to be a little bit more fancy, but this is a great tool. And if you don't have it, I'd encourage you to go to the internet, download this thing, and look at it. It leads you right through the Plan, Do, Check, Act set of things we do. And this, I just throw this up here as a reminder of what a time-weighted average is. As so many times we go out in the workplace and you take a sample for an hour and you get a number and everyone goes, that's it. And you have it, you don't know what was exposed before and you don't know what was exposed after. You don't know if it's a 5-minute exposure. You don't know anything until you've documented it. This is the time-weighted average. I think sometimes we get that number from the lab and we go, this is it. Not all of us, but some of us, and I think I probably have been victim of that myself. Exposure assessment terms, full period, something like, I think it's 7 hours. Partial period samples, grab samples. The listing of samples that I showed you earlier, I have no idea what type of a sample was collected there. Was it a full period sample? Was it just over short periods? Where was it taken? I have no idea. This is all things that need to be documented with what the work we're doing. This is just another visual of the same sort of thing that comes right straight out of that 1977 document. So I encourage you to get that document and review these terms. There are updated documents out there that show this very same stuff. None of it's changed. I just like the 77 version because it's as simple as I am. It just helps me to understand sometimes. Simple, keep it simple, stupid. I'm a believer in that. NIOSH hierarchy of controls, man. Wow. This is a visual that every hygienist ought to have posted on their wall. not just hygienist, but safety person, environmental person, whatever it is that you're doing. This is just a great visual to understand that we don't go straight to PPE, although sometimes that is necessary, but many times we can eliminate. How many times have you been out in a workplace where um, you find out, oh, here's a deal I went to here recently. A noise exposure for an air quenching of a product that was being manufactured. Man, it was creating noise levels well above 90. And it was even infiltrating into the offices next to it, causing all kinds of communication issues and this sort of thing. So we started talking, well, what can we do about that? And everybody was talking earplugs. And I'm going, well, that's one thing, but do we even need to be doing this process? Or why are we doing this process in this manner? So what we found out is that they were blowing air to quench this part, blowing air on that thing at something like 90%. And it only really needed to be done at 50%. So, and I'm not going to take time to explain all that, but what it told me was we could cut back on the amount of time that this process was occurring and prevent some of the exposure. So we eliminated part of the issue. Or maybe you got an acid being used in a process that doesn't necessarily need the same sort of an acid. Can you substitute it? And this process just helps walk you through it. It's a nice little reminder of the things how we can control things. One of the most important things that you need that will support you if you don't have it to support the ARECC process is a strategy, a written strategy. You need to write down what it is you're doing, how you're doing it, where you're doing it, and that will get your processes funded. The worst thing, an engineer who's leading most of these plants, or an attorney who a lot of times is in charge, you go to them without a strategy and you're just talking pie in the sky, they're not going to understand you and they're not going to support you. You just need a written strategy where you get people together and put together your strategy of how you're going to accomplish this ARECC process. Here's another simple diagram of what the ARECC process is. This comes straight out of a book, sampling a book that we've all seen, Occupational Exposure Assessments. This is the process in a nutshell. So let's see, we're at the anticipate, recognize, evaluation, and control. So I'm going to try. I hope you guys can see this. This is a tool that I've used for a long time, and I've developed it over time. It comes straight out of sampling and exposure strategies, which many of us have seen. I've got this thing, I'm afraid to click on anything here and to open up the exact page to where you can see how it moves, but I'm afraid to do that because I'm afraid I'll lose everything else. So I'm not going to do that. But this is something I've developed over the years. It comes straight out of, or very similar to, what's in the occupation sampling set book called, I'm going to go over here in a minute, but I'm going to show you a picture of it. But it comes out of there. And what this is the ARECC process. So this is a simple spreadsheet that I've put together. I know some people in this room probably have computerized functions that do this. I'm here to tell you, those are great systems, but sometimes you just need eyes on. This is an easy way of doing it. This is a particular exposure assessment that I did back in, I think, December 22. Where I went out there, and we all, I think, know what similar exposure groups are now. I put down my group, where this was at, who the person was that I was evaluating, their task, the potential exposures, the quantity. I just went through this whole process, which takes time. But now I can see it. Put down the OELs, exposure rating, came up with an exposure rating. And if you can read that at the top of here, sometimes in this particular case, I had to do a lot of professional opinions because they had no data. And I did the professional opinions based upon what it was I was seeing and hearing. But I had to make an opinion based upon what was the exposure rating, and you give it a number and the basis. You see how this is all spelled out here? This is in a book I'm going to show you here in a minute. And anyone can do this. Not anyone can do this, but you can do this because you got the training to do this. And it's easy for your engineer or your attorney or whoever's running your plant, the risk manager, whoever's out there doing it, somebody with a business degree, they can understand what's going on here. And you come down to health effects rating, which is you can get from material safety data sheets, etc. How certain you are of it. And the important part of this is it gives you a your ranked priority rating, right? So it comes up with a listing of numbers. In this particular process that I'm working through here, it'll give you a ranking of 0 to 30. So what I do is use this, like walk into a refinery and do this process in every operation they've got out there and come up with numbers from 0 to 30. So now suddenly I go to the guy I'm working for or the gal I'm working for and I go, this is what we found. And so maybe all their numbers turns up 16 and below. So now they know where they can spend their money. So instead of doing what that first list that I showed you, where that hygienist had done all these samples, and he just kept doing them every year, apparently, without any rhyme or reason and never putting them into any sort of a risk ranking. Whenever you identify that their exposures are low, you can put them back into this risk ranking and probably lower your numbers. But it gives you an idea of where you can spend your money, etc. It's nice. If you're not doing something like this in your workplace, I can only encourage you to do it. It'll make you a superstar, and it might end up leading to a place where you are able to lead the entire company internationally, if that's one of your goals. So here's a couple of the books that I wanted to show you. The Occupational Exposure Sampling Strategy Manual. I think that's the 77 version that I've been talking about. If you don't have this book here, A Strategy for Assessing and Managing Occupational Exposure, the chart that I just showed you about, all that information's in there. Read that book. Read it, understand it, study it. If you have questions, I'd invite you to ask them now, or my contact information is up here on the screen right now. Give me a ring. Give me a call. Maybe you have a situation in your workplace that you've been concerned about for a while, and you just want to talk about it. I want to tell you, I do that talk with a lot of people. And you'd be surprised that many times, most of the time, I'm learning something new myself. But sometimes you feel like you're in an island, or you're on an island where you're at out there. I just want to encourage you to give me a ring or give one of your peers a ring. Talk to them and ask them about these kind of issues. They got me through at least one and many, many more issues where I was responding to an emergency and didn't know much about the issue at hand. Here is something I want to put on you right here. is when you're putting together a strategy, and that strategy should have the ARECC process in it. Before it happens, your road might look like that. While you are building that road, sometimes it smooths out. You start getting some lines on it and some direction arrows and stuff like that. But many times, after it's been developed, we put it on a shelf and it collects dust. Don't do that. Do the develop it and make it work for you in your workplace. So, without any further ado, I guess we can open it up for questions for a couple of minutes, or you can give me a ring or whatever you want to do. Thank you for your time.
We do have one question in the chat from Jennifer. It's, in your experience, what reference values do you apply for the community?
Well, there's a number of them out there, right? And that's just the AIHA will documents. There's some EPA documents out there. It's just a discussion that you have to have with your the people you're working with and the area that you're working at, and how far out you want to go, etc. There's some DOT references out there. You just have to go through that process and talk to the people who are involved in it. Big train wreck I was involved in. We established some pretty, large circles, or not even circles actually, downwind, upwind, all kinds of stuff, and set some limits up that were available and did some testing. And then you need to not only look at just the testing that you test at ground level, you need to look at, like in a fire, what's going to happen to the material when it starts coming down, and where is it going to come down. So in that particular case, you might end up needing to have a weatherman working with you, somebody who understands how air currents are working. Back in the day, whenever we took out missiles out of the ground, Titan II missiles, we'd have an accident here or there. And when we were taking accidents out, the missiles out of the ground, the team of people I had around me was a weatherman, a pastor, commanders, me, safety people, security people. So all those questions, you can kind of discuss them and start figuring them out. I know that didn't give you a specific number, but that's kind of where I would be at. Is just identify in advance on emergency responses, those sorts of issues. Because if you know you're going to go through a town and you know you're going to have an issue in that town, or potentially an issue there, you need to be planning out in front of that. So, am I good? Did anything else, or are we close to break?
One more question from Jacob. Would you recommend offering BEI testing to the community?
Biological and environmental, you're talking about biological tests, I think. It depends. Again, where the person was. It's in that particular case, like in the Ohio incident, you got a lot of panic in that community, and nothing was thought out before this happened, or it doesn't appear that it was thought out before this happened in the community, or the company who is carrying the chemicals. Right now, they've got to sit down and look at what they've got, what the known exposures are, and what the chemicals are. Some of that biological testing is meaningless. So you need to have a doctor on your team, and that doctor and toxicologist, everybody needs to work together to identify what issues we do need to test for, and if we need to test for it. COVID is a perfect example. We tested everybody for COVID. There's pros and cons to that. We ended up testing everybody. Did we need to test everybody? I don't know. But you need to have it. And there is a national exposure. There is a national um, format and protocol for doing that kind of thing out there. So I just encourage people who have those kinds of questions to, and if you're dealing with those kind of issues in your company, you just need to have done your research up front, or at least as best you can. And most of that's done through a PSM program. Hygienists deal with this every single day because you have people going, "You've exposed me to X, and it's bad news." Well, so you need to have already identified up front how to deal with them, and if you haven't, just start going through the processes that are out there to help you. Are we good?
Yes, thank you, Doug Rush. Now we'll take a few-minute break. We'll be back at 9:50 for David E. Downs' presentation.
Thank you, guys.
Thank you, Doug. Very well done. Appreciate it much.
Thank you.
All right, we'll get started on our second presenter. David Downs has been practicing in the area of environment, health, and safety for 50 years. His experience includes 3M Company, Industrial Health Engineering Association, Controlled Data Corporation, PACE, and EHS Management Partners, which he founded in 1996. In 2016, David founded OERA LLC and developed a process to conduct and document occupational exposure risk assessments. So I hand it over to David to discuss a review of development and current state of qualitative exposure assessment approaches.
Thank you very much. I am looking forward to discussing this subject with all the attendees here. I think this actually works out nicely in the context of the three presentations we have here today. Doug took us through the overall process that we use. I'm going to be talking about qualitative exposure assessment approaches. And I think our speaker coming next is going to be focusing more on quantitative exposure assessment approaches. So I think we're getting a good coverage of the tools and the processes here. So let's take a look at this. And I'm assuming everyone can see my presentation. And so let's go to the first slide here. So this is just the areas that I'm going to try to discuss this morning. We're going to focus on quality risk assessment approaches. And within that, I'm going to cover the types of approaches that have been out there. There are others. There's people have done this for many years, but just start out historically talking about control banding processes that are used in the pharmaceutical area, the NIOSH occupational exposure banding procedure, the COSH essentials, a tool called Stoffen Manager that we'll talk about and demonstrate, and then the occupational exposure risk assessor, and then we'll have time at the end of this for some questions and answers as well. So let's just jump right into it here. I guess the initial question we want to talk about here is why is the industrial hygiene community becoming interested in this approach more? And the reason I think is that the different approaches to doing qualitative risk assessment help solve different industrial hygiene problems. The fact is that there is a lack of established or occupational exposure limits, OELs. I don't know exactly what the numbers are, but I think there's something in the range of 1,000 to 1,200 established occupational exposure limits that have been actually validated, and things like the TOVs from the ACGIH, the NIOSH limits, OSHA, BELs, and so forth. And how many chemicals do we have out there? If you look at the EPA's TSCA inventory, there's something like 88,000 chemicals that are out there in use in the workplace. And so in some cases, we just don't have established exposure limits to help us make the judgments that we were just talking about. And also, in many cases, we may not have a way to actually measure quantitatively. There may be no reliable exposure measurement technology out there, or it may not provide accurate results. So, so how do we make an assessment of what the risk is in a case like that? We'll talk about one of the tools developed by the British, in the Health and Safety Executive. They were trying to provide tools because they realized that in their constituency, there wasn't necessarily the expertise available. And for medium-sized companies, there may not be the ability or the either financially to be able to hire industrial hygienists or safety professionals to help come in. So they were trying to put together a tool that would help them make those risk assessments in those situations. And of course, one of the things we always use in making these assessments is professional judgment. And I know that there's been some studies of looking at how accurate our professional judgment is, and quite frankly, it's not what it all is what it should be. And so we may need to supplement our professional judgment by using a more definitive tool to help us categorize and qualify the risks that we're doing. I think it's also, and Doug touched on this in his presentation, it's really not an option to sample everything that we have in a workplace. It's not economically effective, and we need to prioritize our time and the money spent as we go through our processes to figure out what are the most important potential exposures that we need to sample and focus our time and energy and quite frankly our financial resources on those things that have the highest risk of being an overexposure situation. So there's a number of different reasons why we may utilize qualitative risk assessments to help us get down that road a little bit further. So let's talk about some of the terminology that's used in qualitative risk assessment approaches. You probably heard of the term banding, and that is a very common terminology that's used in many of the risk assessment approaches that have been developed and that have been used. Banding basically means we're instead of looking at a specific value like a PEL or a TLV for a particular chemical, we may create a range of values as opposed to that single value and apply rules to the range of values rather than the specific value itself. We always say that a TLV is not a hard and fast number in terms of safe and non-safe or healthy and unhealthy. We have to look at it, a lot of other factors associated with it. Banding sort of gets into applying perhaps controls in some cases. In other cases, maybe determining whether or not we need to do sampling to a range of values rather than specific, if we don't have a specific value to work with. So we're going to talk about 4 ways of going about doing this. One is control banding. The other is hazard banding. exposure banding, and then finally exposure risk banding. So let's talk about those in terms of a little bit better definition here. So control banding, which was initiated in the pharmaceutical industry, uses information about the hazard or toxicity of material to create categories of increasing hazard. And then we assign industry-specific controls appropriate to each of those categories rather than to individual numbers. We'll talk more about that, each of these as we go forward here, but that's the basic definition of what control banding is. We're applying controls to a range of toxicities or hazards that we have information about. Second is hazard banding. So in this case, we're using information about the hazard or toxicity of material to create categories of increasing hazard. And we'll talk about the difference between this and control banding as we go forward as well. Then there's exposure banding, which here what we're trying to do is use a variety of factors which tend to affect the exposure level in an algorithm to create bands of increasing exposure. So here we're not necessarily in this case looking at the hazard of the material. We're looking at what's the potential for having what's the potential for having an adverse exposure as a result of using this material. And so in these cases, we'll evaluate certain factors such as, for example, volatility of the material or dustiness of the material, as well as how we're using it, how much we're using, how long do we use it, and try to get to an estimate of or at least a picture of what the exposure to this material might be. And then finally, we'll talk about exposure risk banding, where what we're doing there is really putting together both of those approaches. So we're combining a hazard band for the chemical that might be in use and an exposure band for an operation using that chemical to estimate the exposure risk level. So this is based on the classic risk definition of hazard times exposure equals risk. So here what we're trying to identify is the risk associated with it based on both the hazard of the material and the exposure risk that we have as a result of the way we're using the material. So the first area that I'm going to talk about here is control banding, and really it's appropriate to start with this particular concept. It was really the first attempt that was made back in the late 70s and some companies in the early 80s and the early 80s. And primarily in the pharmaceutical business. So pharmaceutical companies started developing an approach called control banding. The problem that control banding helped to solve for them was that in the formulation of the new medicines that the pharmaceutical companies were trying to develop, and this also came at a time when there was a rapid increase in the number of chemicals that were being looked at as medicines. But for many of those, the active pharmaceutical ingredients or the APIs had really no established exposure limits, and oftentimes also had no established industrial hygiene monitoring methods. And so they were really facing a very difficult situation because the choice was to apply a maximum control for everything that they were working with, which would be very difficult to do both technologically and also economically. We already know that the cost of medicines are very high. So what they started to recognize is they often did have some data on the hazard of the materials. As they began the process of analyzing by necessity, they would have to identify, well, what's the effective dose of this material? Well, the effective dose can be an indicator of the toxicity as well. And so in some cases, they did have some information that they could use to help assess the materials that they were working with. Let's take a little bit closer look at that. And so the process was, first of all, assign a compound to a hazard band, and that would be based on available toxicity data. It was mostly generated in-house. I will say, though, that many companies are now going out of their organizations to contract with companies that are focused strictly on doing different types of testing to assess the toxicity and the therapeutic effect of chemicals that are being submitted, so that they can do it more quickly and get data more efficiently. So whatever available data we had, then those would be would put that material into a particular hazard band to correspond to a range of airborne concentrations. And we'll talk more about this, but in almost all cases, what we're talking about here is looking at the respiratory exposure route as being the approach that we're trying to control. For each of the hazard bands that are developed, a set of controls would also be assigned to each of those bands. So that would include, the full range of things, including engineering controls, administrative controls, and PPE perhaps, to a particular band. And we'll take a closer look at what that looks like here as well. So this is an example of what the hazard bands look like. And this is there's multiple models that companies have developed and used. There are some very good consulting organizations who have also put together models based on some of these criteria and additional criteria as well. So, for example, you might look at what's the potency of the material, and so in terms of milligrams per day as a dose, if it's so if it's greater than 100 milligrams per day, that's pretty high. So it means it's not a highly potent material. And then as you get to higher concentrations in terms of milligrams per day, to a point where the potency is less than 0.01 milligrams per day, that's something that is highly potent, and therefore would be in a higher band. So you can sort of see that the bands that they established in different models in terms of how many bands were used. Some organizations use 4 bands. Some organizations use 5 bands. In this case, we're using 5. So it goes from materials that are considered relatively safe at band 1 all the way through band 5, where materials would be considered particularly hazardous. So we might also look at, if we have it, we might have acute toxicity in terms of oral LD50s. That would be an indicator of the hazard of the material. Other fairly simple tests that could be quickly done: irritation. If it's not an irritant at all, then it gets into band 1. And if it's severe irritant or actually corrosive, then it would get in the higher bands. Some other organizations also used whether or not there's cumulative effects, and if there's no cumulative effect of exposure to the material, it gets a lower band rating. But if it does have cumulative effects, then say high cumulative effects, it gets into the higher band. So again, we're using whatever data we maybe have available to ourselves. Some organizations will, if they're really starting out with a new chemical, new material that they don't really have any data on, they may handle it as initially as a band 3 in terms of the controls that we'll talk about in a moment here. But I would say that we're getting better and better at being able to, because there's a larger number of these chemicals, many of them are quite similar in terms of chemical structure. So you may even be able to look at the chemical structure of the material, which you'd almost always have data on that, and compare it to other chemicals that are similar in terms of the structure, and make some at least initial judgments based on that, and that might drive you to a higher band. But most would start out with a band 3 at least in terms of controls. So that's a hazard band, but the control banding piece really is based on the idea that depending on the band that's assigned to a particular material, that would determine what types of controls you need to have in place. So, for example, if something is in a band 1 or band 2, it's relatively less hazardous. So you could even have transfers from materials through open scooping of the material with local exhaust ventilation. That might be allowable in handling these kinds of materials, because the exposure potential the exposure risk is relatively low. However, if you get into bands 3 and 4 and 5, as you can see, that wouldn't be allowed in those cases. So these are rules that these organizations put in place as they were developing their manufacturing processes to help define what level of control do I need to put in place for these materials. And remember now, these are materials where we don't really have occupational exposure limits. If we have occupational exposure limits, it's a different story. You don't have to kind of think about this banding process. But these are cases where we really don't have exposure limits, or maybe we don't have even ways to measure what the exposure level actually is. So we're depending on putting in place engineering controls in most places. So you can see on the left-hand side there, you've got open screw conveyors that would be used perhaps up to band 3. These alpha beta valves, which essentially isolate the flow of materials, could be used up to a band 4, but not a band 5. So the reason for that is that an alpha beta valve does a good job of enclosing the material. It's a valve that's physically attached to both the supply and the process container or reactor. But in materials that are in band 5, you have to be concerned about the internal contamination of those parts, and having to, how do you change them? How do you prevent exposure? So that may not be available for a band 5 material. Glove box or isolator can be highly effective, as well as vacuum conveying in a closed system for even high-level band 5 type materials. You can see a description of the overall controls at the bottom there. For band 1 in general, you're talking about using good manufacturing processes, well-designed manufacturing processes for handling the materials, for transferring the materials. Band 2, you'd want to have good manufacturing processes, so you'd also want to have local exhaust ventilation applied as well. For band 3 materials now, you're starting to talk about enclosing materials, enclosing types of approaches. So ventilated enclosures, for example, like our typical laboratory fume hood would be a good example in that case. When it gets up into band 4, then we really are starting to talk about systems that completely contain the material, and we don't really have any normal exposure to those. And with band 5 materials, we may be talking about remote operation. or robotics in some cases, so that we are separating the people that are running the process from the material physically and doing it by using remote operation. So that's control banding. That's the process that the pharmaceutical folks use. Let's talk about advantages, disadvantages here. Advantages is that this was generally considered effective in preventing adverse exposure. The algorithms and the decisions were generally made in a very conservative fashion. It was considered effective. It doesn't require detailed tox data or OEL development before you can actually use the material, because that would really pretty much shut down the development process. The disadvantages, it's generally considered a conservative approach, as I said, and that's appropriate. It's appropriate for this because we're making judgments on a qualitative basis, and coming out using a conservative approach is really what we need to do. But that's going to cause you to probably put materials into a higher level of control than they may actually need once we find out the details in terms of toxicology. We may have overshot the control, but if we don't know it, it's appropriate that we be conservative. The other thing that I think it's very important for us to understand is that because the pharmaceutical industry uses very specialized equipment to contain, to transfer, to process these materials, the controls, it's applicable really only to the unique set of hazards and controls common in the pharmaceutical industry. And so we'll talk about an approach to try to address that in one of the other examples that we've got here. But when we're talking about control banding and the types of controls, those are generally applicable to pharmaceuticals. They may also be used in some cases in just general chemical manufacturing as well. But it'd be hard to transfer that type of approach to some other completely different manufacturing process. There would just be a different set of controls that would need to be considered in those cases. So that's advantages and disadvantages to control banding. So let's move on to the next area here. And what I'm going to go to is a description of the NIOSH occupational exposure banding process. So the NIOSH process has really been relatively recent. They started working on this probably 10 to 15 years ago, maybe less. But the reason was that NIOSH recognized what we talked about earlier. They were concerned about the significant lack of authoritative, in their terminology, occupational exposure limits. So based on the TSCA inventory we discussed, there's over 85,000 chemicals listed, and there's more added every year. But there's only about 1,000 or maybe 1,000 to 1,200 authoritative occupational exposure limits. And by authoritative, I think what they're talking about here is they've been reviewed in a systematic manner, such as was being done by NIOSH, for example, in coming up with the recommended exposure limits that they have, but also the other organizations like ACGIH that have a process and controls in place to ensure that the process is being followed to develop those their TLVs. So what do we do about the other 84,000 chemicals that we potentially have in our workplaces? So what NIOSH wanted was a consistent and documented process to characterize the chemical hazards. So let's talk about how they go about doing that. So NIOSH has proposed 5 bands, and they classify theirs as A, B, C, D, and E. And each band is associated with an airborne concentration range. So particulates, as you can see here, so anything that has a airborne particulate range, that control it's greater than 10 milligrams per cubic meter, or greater than 100 parts per million, then that's considered a material that would be assigned to the lowest occupational exposure band, or the A band. And then as the concentrations increase, you can see how they've decided to establish their bands. And basically it's the rule of 10 that they're using in these cases. So that gets down to, in the case of particulate concentrations, things that have an exposure range of less than 0.01 milligram per cubic meter would be assigned to an E band, and so forth with the gases and vapors. So you can see the ranges that they established in their model. They also put together what they called a 3-tier development process, and the tier 1 was intended that really an industrial safety, industrial hygiene generalist would be able to implement that process, and we'll talk how that works in a second here. But it wouldn't require a lot of specialized information and knowledge in order to be able to do a qualitative assessment at the tier 1 level. Then tier 2 level, there you're looking at using trained occupational hygienists to look at the information that's available. You look at how much information do we have available about the material in the first place. And so that would be the semi-quantitative. And then tier 3 would be for materials that we really don't have a lot of information, and might require us to use a toxicologist or to help do the assessment. And so those are the 3 tiers that they established as means of assessing what level of data you might need to do. So let's talk about the tier 1 process. And so first of all, this would be a situation where the chemical of interest has no occupational exposure limit. So the first step then is to look at the global harmonized standard hazard codes in categories in recommended databases. So you look at the safety data sheets, for example. I would, if you're looking at pure chemicals, I would highly recommend looking at Sigma Ulrich as a resource. I found their safety data sheets to be really the best in the business. And then there's a thing called the Justice Database, which is maintained by Germany, the government in Germany. It is an excellent resource for obscure as well as common chemicals, and really is kind of similar to what NIOSH used to have as the database of basically all the information we know about or have availability to for a particular material in terms of toxicology information, usage information, and other safety information. So then you compare those hazard codes and categories with the NIOSH criteria for each health endpoint. And there is NIOSH has provided a worksheet with those criteria in there. So it makes it, they've gone through the process of identifying given what the hazard codes are, work through it in terms of one of those 5 bands. And then finally, you assign band for each relevant health endpoint based on the criteria. In this case, the bands A and B, which are the least harmful, are not really used. And part of the reason for that is that I think they're concerned that materials would be inappropriately assigned to a band A and B when it should be at a higher level band. But that tends to, I think, reduce the accuracy of the process here. And then so you'd have to start at a band C as the lowest available band for tier 1. And if you wanted to go further in this process, you'd have to go to a tier 2 process or a tier 3 process in order to be able to assign it to bands A and B if that's appropriate. So that's kind of the process that NIOSH uses. Let's just in terms of, and this is information is out there. If you Google NIOSH occupational exposure banding, there is a full user manual that discusses the process and gives all the background and gives the tools that you need to be able to use. They do have an electronic spreadsheet type tool that can help do the process as well. It's publicly available. That's a major advantage. Provides a consistent process, and it's more precise than control banding. Would give you a tighter band than control banding might give you, because essentially you're working with a higher level of information, particularly with respect to being able to use the hazard statements on safety data sheets and other sources, as we discussed. Disadvantage is that using the easiest way to go about doing this, using tier 1, the highest band available is band C, and that is a range of greater than 0.1 to 1 milligram per cubic meter as a control level, or greater than 1 to 10 parts per million as a control level. So it really puts pretty low numbers out there if you're just using tier 1. The thing that I have concerns about is that their process uses hazard statements that are not related to inhalation exposure. And clearly the results of all this in terms of concentrations are inhalation exposure situations, but NIOSH also uses hazard statements that may relate to, for example, eye exposure, eye toxicity, or skin hazards. And so you may have a material that from looking at it, if you look at the hazard statements that are directly related to the airborne respiratory route, some of these may be relatively less hazardous from that standpoint, but they have a high hazard from a corrosivity standpoint, for example, and would tend to increase or actually decrease the recommended exposure level. You throw it into a higher band on that basis, but those statements don't really relate to inhalation exposure at all. So there's the other disadvantage is there's no assessment of exposure risk. And so what the process that NIOSH has developed is a very good process for doing hazard banding. So I see that as a little bit of a limitation on that approach. So that's the NIOSH approach. And let's move on, and we'll go ahead and talk about the COEH essentials. So control of substances hazardous to health, or COEH, is something that was developed based out of a set of regulations in the United Kingdom, the Health and Safety Executive, regulations came out in 2002. So what the HAC basically said was that if you're using chemicals in your process, you need to do a risk assessment. And so what they recognized was that for the majority of enterprises that would be caught up in that requirement of having to do a risk assessment, there was really a lack of expertise in general for the small and medium enterprises to do traditional industrial hygiene assessments. So, so they started working on putting together some tools and approaches to help these smaller organizations do an industrial hygiene risk assessment. Let's talk about that a little bit more here. So the COSH regulations required that companies perform risk assessment and control risks that are not acceptable. And the HAC developed and provided an online tool called the COSH Essentials to help them do that process. The tool assigns substances to hazard bands based on their toxicological classifications, or H statements in general, from the safety data sheet. And it's also then based on the hazard band assignment and some factors related to potential exposure, the process is assigned to a set of controls, and these are very industry specific. So this is interesting because this was an approach that they developed that's similar to control banding, but because they developed recommendations for controls for a variety of different industries, they were able to expand the utility of what essentially was control banding from the pharmaceutical industry to expand it to cover a lot of other industries that were important in the British organizations. So this is what their bands look like. And they used a 5-band approach. And so an A would be, you can see the kinds of acceptable concentration ranges that the A band would cover. Slightly different than what NIOSH has, but very, very similar. And again, it gets lower acceptable concentration ranges get assigned to a higher hazard band. What they what they did was they assigned specifically hazard statements. If you had hazards, if you looked at the safety data sheet, then the hazard statements, if it was a 315, 319, or 336, that would get assigned in an A band. And so it helped standardize the process, similar to the way that NIOSH did a little bit later, but they assigned these hazard statements to particular bands. And so it would, for example, if you ended up with say 301, 311, 314, and so forth, then those would get into that C band category. And then on the right-hand side, they would talk about generally what kinds of controls you would need. And those are, again, similar. Now, what they did was, if you had hazard statements, for example, 300, 310, 330, and those are all different reflections of the hazard of material, higher hazard. They sort of backed out of the process at that point and said, okay, you need to, at that point, if you're handling those kind of materials, it's in a hazard band D or perhaps a hazard band E. Some of these hazard statements reflect carcinogenic types of health effects, sensitization, and so forth. Those they said, we're really not going to be able to help you there. You're going to need to, if you're going to use those materials, you need to go out and get an expert and have them get involved in determining what are the controls that you need to have in place for those materials. So that's sort of the way that it worked fine for A, B, and C, but D and E required you to go out and get some more help. So the thing that they did then was they developed these industry-specific guidelines, and there were 19 in all, and you can see some of the ones that I've put in place here, but there's actually 19 total. And then for microelectronics, let's just say, if that's the one that you're dealing with, they would have worksheets similar to what's shown on the right-hand side there, but would be cover advice for managers, and then would get into specific different types of processing, so wet etch, chemical vapor deposition, and so forth, that would have separate guidance sheets for each of those processes. And these guidance sheets are actually quite nice. They do tend to be a little bit generic, as kind of would be necessary, but if you're in a business of working in microelectronics and you're using chemical vapor deposition or in ion implementation, these are nice data sheets that are really quite useful to understand what are the potential hazards with the materials you're working with and the processes that you're dealing with. They do have an e-tool, and I'm not going to go into that in great detail, but it allows you to come up with a name for a process, and it goes through a number of different steps. But ultimately, it's going to come up with a general recommendation and so forth. You can see on the bottom portion of the right-hand side here, the recommended control approach is general ventilation in the example that we used here. And then there's actually a general ventilation guidance sheet that gives you some basic information about general ventilation. So these are nice tools, even if you're not using the process or doing the banding part of this thing. If you've got situations that apply here, there's some information that comes into play. So kind of useful. So advantages, disadvantages of the COEH Essentials. One, it's available freely on the internet. It's relatively easy to use from safety data sheet information. And then they provide a lot of links to advice and recommendations for controls that can be used. Disadvantages, I didn't get into it, but it does have limitations in the number of the types of agents that can be assessed. Again, they're using hazard statements that are not related to respiratory exposure. I just quickly go back to the chart here. You can see in this case that any of the 8 statements that I've highlighted in blue are actually hazard statements that are not related to respiratory exposure. So you're classifying the hazard of the material for respiratory exposure using hazard statements that don't have anything to do with that kind of exposure. The exposure risk assessment is limited, and it tends to bias toward a higher level of control. So it's a trade-off between complexity and accuracy in this case. So it's simplifying the process, but it tends to bias toward a higher level of control. So that's the trade-off that you would have to make there. So let's go on to talk about the last 2 approaches here. A software manager is a product that was developed in the Netherlands and is widely used in the EU. It uses an approach similar to hazard banding as is used in the COEH Essentials. But they've enhanced the exposure banding process. Vapor pressure is being used to assess the potential for exposure to vapors from liquid materials. They also assess dustiness of solid materials. They assess how it's being handled, what level of ventilation is applied, it does assess whether or not and what type of PPE might be used and so forth. So again, so it results in the assignment to one of 4 exposure bands as a result of this exposure banding process. Now, the hazard band and exposure band are combined. So in this chart here, so you've got your 4 exposure bands that would that are established. You've got your 5 hazard bands, and the way that they use this is that they determine they're trying to give you what is the highest priority in terms of doing further evaluation. And so if you've got something that's a hazard band, let's say D, and is exposure band 3 or 4, that's going to be in a higher priority. And so it establish that of the processes and chemicals that you're assessing, these are the ones that you really need to focus on. So there's a higher level of focus of what needs, which ones need to be assessed further. They do have a tool, and I won't go through this in great detail, but it just leads you through a process of answering a series of questions. Is the product a liquid or a solid? What is there any dilution? What's the process itself? What's the duration of the task, and so forth? Is respiratory protection applied? It goes into some very simple modeling in terms of the area. And then finally, it will result in that identifying that hazard class and exposure class, and ultimately coming up with a risk priority. So in this particular case, it came up with a second priority to improve your exposure situation. They also do provide you with some ideas and tools that can be used to reduce that impact. So they, similar to the COEH Essentials, they provide some guidance and what can be done to reduce the exposure risk as well. So a nice tool. There's no fees for the lowest tier of user. It has better exposure banding capability. It does have a large user base, mainly in Europe. Again, unfortunately, in my view, it uses H statements that are not related to respiratory exposure. So that's going to bias it in some cases to a higher, requiring a higher level of control for things that are not related to respiratory exposure. It does have, if you work through this, the tool, it does have a fairly high data input requirement. And my concern is that, well, it's really a fairly sophisticated tool. It has relatively complex algorithms. It really boils down to 3 exposure risk bands, and those are those priorities that we talked about briefly here as well. So it doesn't give you a lot of choices. It just says, here's priority 1, 2, and 3. So it sort of boils things down to that level. So I'm going to go through one other tool here, which is the Occupational Risk Assessor. This tool includes both hazard assessment and exposure risk assessment, similar to Stoffer Manager. Hazard assessment score from 1 to 5 is based on the OEL, if you have that, or on hazard statements. If you don't have data, actual OELs or hazard statements that are related to respiratory exposure, then you may need to go into looking at toxicology data that may be available for that material. Then it also uses an exposure score of 1 to 5 based on volatility or dustiness of the material and 4 other defined criteria, which we'll talk about momentarily. And then you multiply those together, you get an exposure risk score from 1 to 25. Now, the real purpose of this tool is to, as you're doing your, trying to put together your plan of attack, your industrial hygiene strategy, It's to provide guidance as to whether qualitative exposure assessment is needed for a particular workstation and use of a chemical. So what we're trying to do is to identify where do we need to spend our time and effort in doing qualitative exposure assessment, and which operations and which chemicals can we maybe take at a lower priority, or maybe we just document that there's really a low risk of exposure to those materials, and we focus on those that are higher risk. So that's a primary purpose. So it's a tool. It's based on a SQL Server database. There's no limit to the number of users. You can set up a model of your organizational structure so that you can keep your data based on areas and operations that you have. Users, you can limit users to access only parts of the organization they're responsible for, and then there's various security levels as well. So I'll walk you through some screenshots here. So this is the hazard score development. So you identify the material, put in the ID, which in this case would be the CAS number. This particular part of the hazard score development is something done by experts in ORA on a one-time basis. Really, you do that hazard assessment, and unless some data changes, you don't really have to modify it over time. The volatility component there is a range, again from 1 to 5. It gives it a score. The higher the score, the higher the volatility, and that's based on the vapor pressure. Then you have an opportunity to input actual OELs that maybe exist. If they do exist, then they're assigned to a range, and you'll see real similarities between these hazard ranges and what you've seen in the other types of tools that are out there as well, very similar. And then you, going off of the safety data sheet, or perhaps looking in Justice or some other database, identify what hazard statements have been assigned based on GHS. And the system uses an algorithm, and uses, so if you, for example, if you click on H330 fatal if in hell, that automatically sends it to the hazard score of 5. If it goes to a hazard score of 331, toxic if it hell, then it would get a hazard score of 4, and all the way to harmful if in hell. So you can see that based on the selections of the hazard scores, hazard statements that are applicable to the material, that's one way to classify the material. And if you just went on the basis of the OEL, it would be scored a 2. But because some of these, for example, 373 have a higher level of hazard, this one gets xylene gets a hazard score of 3. We put in the other exposure route hazard statements, but those are not used in the algorithm to calculate the hazard score. There's only the hazard statements appropriate to respiratory exposure are used. And then the next piece of this is to be able to do a workstation exposure risk assessment. So you're looking at, you define what workstations you're using chemicals at, and you do an assessment on those. And so, for example, this one here is adding raw material to a mixed tank, and it's using bentonite. So the quantity used is a factor. And for each of these factors, energy added, exposure duration, control status, and particulate generation, there are definitions similar to the one you can see here. This is the guidance to assigning the energy added component off the assessment. Each of those factors are then multiplied or averaged, I should say, to get an exposure score. In this case, the exposure score is 2.8. The hazard score comes across from the identification of the material itself. In this case, bentonite does have a high hazard score because it has silica in it. And then you multiply the hazard score times the exposure score and get an exposure risk score of 14 in this case. Now, how that's used is defined here. And so if the exposure risk score is 1 to 5, it's insignificant and no exposure monitoring is really recommended. If it's 6 to 10, again, same thing, unless you make changes. In this case, it got a score of 14, so it would be one where you would want to plan to do quantitative exposure monitoring in the intermediate term, say 12 to 24 months. If it was a 16 to 20, you'd want to do that right away. And if it's over 20, then you don't really need, you don't do anything. Don't worry about doing exposure monitoring. You need to take actions immediately to reduce exposure factors as soon as possible. So that's how the 1 to 25 score comes into play. So again, advantages, disadvantages of this tool. Advantages, hazard scores are developed by experts. We would have those pre-populated and assessed. And it only uses H statements related to respiratory exposure in those situations, or tox data as needed. Really, the workstation assessment is designed so that it doesn't require a detailed industrial hygiene or safety experience. Really, it's anybody who has a good knowledge of the process and can observe how it's being done and worked can do that workstation assessment. So it could be, you can spread the labor related to doing the workstation assessments to a broader group of people. And it is enterprise scale. That's disadvantage is limited to the respiratory route risk assessment. If we wanted to develop tools for example, skin exposure, you could certainly do that, but that's not what this tool does. It's limited to that respiratory route. The workstation assessors need to be trained and calibrated in their judgment using the guidance that is provided. And it does require a license to use based on the number of chemicals and workstations assessed. So there's some costs associated with it. So advantages, disadvantages there as well. So that's where I'll leave it at this point, and would just ask if there are any questions that we need to address.
There's no questions as of now, so
Okay.
we can take let's see, we can be back in 5 minutes to start with our next speaker, Bruce Nauman.
Okay, so there are 2 questions there.
Yeah, I did see one that came in late.
Yeah, so just give them a little bit of time.
Should I do it before or at the end and do their questions first before?
These questions, now we're gonna let them be and see if we can ask them the questions and if we can answer them. Now, when the other one finish, just give them a little bit of time to see if anybody has any questions, like a minute. No question, then let's go for a break. Well,
That's the last one, isn't it?
the last one we are going, we finished.
Yeah, this is, well, we're doing the last one.
Yeah.
Okay. So should I have
This one-
David answer this question or have it answered at the end? Because it came in
At the end.
at the end?
Probably,
Okay, and
yeah.
I'll let him answer first
Yeah.
before we get to the other questions.
Yeah.
Okay.
So do we answer it now or later?
If you can answer it now.
Okay, sure. So I think the one that we've talked about, which tool works best for mixtures, and it the control banding is really focused on strictly single chemicals because of the nature of that particular development. The rest of them, because they use H statements to do the hazard banding portion of the process that they have to do that portion of the process. So the way that the GHS requires that safety data sheets be put together is that if you have a mixture of materials, then they have rules for which H statements apply to the mixture overall. So you're really depending on the ability of the people doing the safety data sheets to use the GHS process and assign those H statements. If they've done that properly and you use those H statements, then all the ones that are using the H statements can handle mixtures. And I'd have to say that over the years that I've looked at safety data sheets, they are getting a lot better. But I would, if you're doing that process, I would highly recommend that you, if you've got a mixture, try to look at multiple manufacturers' data sheets to see if there's consistency in the way that's done. And again, you do have to use a level of professional judgment to assess it. And in the end, that's one of the reasons that on the ORA side, that is all done by experts in toxicology and industrial hygiene. So but I will say that the safety data sheets in general are getting a lot better in these days. And I haven't done any comparisons to see if the results are similar. In general, the ones that use H statements that that are not based on respiratory can be a little bit overly protective. I'll just leave it at that.
Okay, thank you for that, David Downs. Next, we have our last speaker for the seminar. It is Bruce Nauman. Dr. Nauman is a retired toxicologist. He was formerly executive director of toxicology in the Global Safety and Environment Group at the pharmaceutical company Merck & Co. He is a member and former vice chair of ACGIH Chemical Substances TLV Committee. And Dr. Nauman will be presenting health-based exposure limits, basic methods, and new approaches.
Great. Well, thank you for the invitation. It's great to be here, and I'm glad I'm following the talks by Doug and David, because I'll be trying to pull through some of the threads that you learned from both of those talks. I'm going to be talking about health-based exposure limits. And I appreciate, the opportunity to do this. Dennis Casserly is on the organizing committee and called me a few weeks ago, and I jumped at the opportunity because we're as part of the TLV committee, we're trying to do more outreach and always looking for opportunities to share our knowledge, et cetera, with industrial hygienists. So, and I will plug the ACGIH's Learning Pass program and series of webinars that they have. And we're going to actually do 4 of these toxicology related things in the fall. So stay tuned for that. So today I'm going to be spending time talking about how we actually set health-based exposure limits. It'll be at a pretty high level, but I'll give you enough details to give you a sense of how the sausage is made. And try to communicate how the OELs or the TLVs are used typically by industrial hygienists in their jobs in the course of doing occupational health risk assessments. Obviously, reading the documentation is very important, and that's something we encourage. I do also want to talk about some of the new things that have been happening around signing notations, and specifically, well, we split SEN into DSEN and RSEN a number of years ago. Skin notation has been around forever, but we introduced a new ototoxicant notation. So I want to say a little bit about that and spend some time at the end talking about how we're beginning to set surface limits, TLVSLs, and hopefully you'll come away with a good understanding of how all these things are working. So, we heard Doug talk about the ARECC. There's, the terminology differs a little bit depending on where you're, which website you're looking at. And even in risk assessment, there's a lot of commonality between the kind of the buzzwords or the descriptors that we have. And so up here in the upper left, we have hazard identification and dose response assessment. And that's by and large what what is happening when we're setting the numerical occupational exposure limits. And of course, that has a lot to do with hazard, and then it passes over to the evaluation, et cetera, and around all the way through risk management and control. So they all link together, and it all starts with setting the OEL. So what is an OEL? I think we're probably all pretty familiar with this definition that comes out of the TLV book. It's an airborne concentration that below which you wouldn't expect to see any adverse effects, even if you work with a compound for your entire working lifetime. And it's not preventing any effects, but clinically significant changes are really kind of adverse effects. And so there may be minor effects that happen, but the goal is really to identify the point where we wouldn't expect to see any adverse effects. So the process after reviewing all of the available data is to try to identify the critical endpoint, which serves as the basis for the OEL. And that really is the first adverse effect that you see as you start going up the dose response curve, or as the exposure is increasing. And we try to identify a no effect level for that endpoint, and then apply various safety or uncertainty factors. The terminology has changed over the years, and we tend to use adjustment factors now, but we're really talking about various sources of uncertainty and variability, inter-individual variability, interspecies extrapolation, depending on the data set and what the data that we're extrapolating from. And ultimately, we're really trying to come up with an acceptable daily exposure. And then as you'll see, at least with an occupational exposure limit, we tend to divide that by 10 cubic meters, which is the average amount of air that a worker breathes in 8 hours. And we're introducing the new TLV surface limits, and essentially that would be dividing it by a standard surface area of 100 square centimeters. So as I mentioned, the first step is to do a literature search and make sure we have all of the available information at our fingertips to review. And we tend to focus on trying to understand what the compound does, what the mode of action is. Obviously, we're interested in any acute toxicity, if it can cause irritation, sensitization. And really, it's very difficult to set numerical limits with limited information like that. Unfortunately, as David pointed out, we have several banding schemes that we can use to get us through those situations. But more often than not, we have a wealth of information about repeat dose toxicity, maybe out to chronic or 2-year carcinogenicity studies. We like to see data on effects on reproduction and development. And I mentioned, mutagenicity is obviously, genotoxicity is a key endpoint, and we certainly pay attention to carcinogens. If we're lucky, we also have access to some information in humans, whether they're case reports or epidemiology studies. And of course, in the pharmaceutical industry, we have the luxury of a lot of human data coming from clinical trials, and that made our lives much easier when we were doing this, at least for the compounds that got to, if they got to that point. So looking at the endpoints, we choose the point of departure and for that critical endpoint. And so what we're trying to identify is the no observed adverse effect level, if we can find one, before we start applying adjustment factors. If we don't have a NOEL, we'll use the lowest observed adverse effect level, or the low L. EPA tends to use, and there's been an increased use over the years of something called the benchmark dose, which is a curve fitting exercise that identifies the response rate, 10% response rate. And usually there's some statistical lower bounds on that people tend to use as the starting point. And the BMD-10 it's probably, I mean, you could argue that it's a NOEL, or right between a NOEL and a low L. So think of it that way. If we only have a NOEL or a low L, these are non-adverse effects, they can be used, and that happens sometimes in the pharmaceutical industry, but you generally don't need to be thinking about using all of or as high a composite adjustment factor in those cases, because the effects are not clinically significant, and you only have to go a little bit lower to prevent any effects. So this is the general equation that we use. And so the OEL is the NOEL, sometimes corrected for body weight if it's coming from an animal study. We assume 50 kilograms typically, sometimes 70 is used. And then it's adjusted lower by a number of factors. And the AF sub C is the composite adjustment factor. And the next slide, I'll go through the individual components of that. Sometimes a modifying factor is used, and that allows for infusion of professional judgment. The volume of air, I mentioned 10 cubic meters. And then if the data are available, we'll do some pharmacokinetic adjustments. And S stands for the steady state adjustment factor. And alpha is a bioavailability correction factor. And I'll say a word or two about those in a second. So there are various sources of uncertainty and variability that we consider. The first one's inter-individual variability. Way back in 1954, Lehman and Fitzhugh from FDA coined the term 100-fold safety factor, and that ostensibly was 10 for human inter-individual variability and another 10 for interspecies extrapolation. In the early mid-80s, the EPA came up with a series of uncertainty factors, as they called them at the time, typically factors of 10. And as the folks, the toxicologists in the pharmaceutical industry got involved with these discussions, and we were asked to, come up with the pharmacokinetic and pharmacodynamic data. That's what PK and PD that we've been kind of sitting on. How can we improve the process? So the term chemical specific adjustment factor was coined. And so that's where we leverage the data that we have on those to move away from default uncertainty factors, or sometimes called data derived. Anyway, even with the animal extrapolation, they've moved away from straight numbers to considering allometric scaling, which is really the ratio. It's the volume to surface area ratio. Or if we have data, chemical specific data, we'll use that. The low L to no L, if you only have a low L, and these are just examples, you can think of perhaps a factor of 3. I think EPA was doing that. Subchronic to chronic, when you look at a large number of studies, the ratio of the no Ls from a chronic study versus a shorter duration study is more like a factor of 3. And we published on this some time ago. And actually, David Dankovic was the lead author on a paper that we at NIOSH about 5 years ago, where we went through the scientific basis of these uncertainty factors. Route-to-route extrapolation, if you're going from animal data, and David was lamenting about how some of the hazard statements were really oriented toward the oral route and not necessarily inhalation. And obviously there are big differences in how much could be absorbed orally versus through the lungs, if because of the thinness of the air blood barrier. There's database quality and completeness. How good were the studies? How consistent? So there are other factors that come in, modifying factor, even less than one. If the data in a particular study an animal model may not be all that relevant to humans, maybe you'll even have a number less than one, which would increase the OEL a little bit if you use that. But we have all of these factors that we need to consider and decide which ones are appropriate. And this is if you're using them kind of rotely, which nobody does, but and especially in the TLV committee, these are all things that people have in the back of their mind. They're aware of these. They've read the papers, but the process is more general. I think it's been in the past described as the Delphi process, where if you have 25 people sitting around the table thinking about the same data set, you tend to iterate to the right number, if you know what I mean. So a lot of professional judgment is leveraged there, but these considerations are certainly in the minds of those individuals. So I mentioned pharmacokinetic adjustments. If you have a compound that's accumulating over the course of a work week, the blood levels are going to go, trend higher. So if you have to set an OEL based on a single dose study, you need to adjust for the fact that if they got it, 5 days in a row, it's going to lead to higher blood levels. So if you look at the peak and the trough there, that ratio is the S. So you would divide by that much in that equation to account for the potential accumulation during the work week. If you're setting the limit based on a chronic study, then you've already reached steady state. It flattens off. As if this went off to the right, it would flatten off. So you would know the no L or the low L that you got would be, you could just use that directly. You wouldn't have to do the adjustment. Depending on which route you're talking about, maybe it's just an oral study, and you see here absorption directly from the GI tract into the blood on the bottom is maybe limited for some chemicals, whereas if you breathe it in and it comes through the respiratory tract, whether it's a vapor or even small particles that can get down into the deep lung, maybe medium size, slightly larger that could deposit in the conducting airways. There's absorption from all of those parts of the lung, and ultimately, it goes up and gets swallowed if it's not absorbed already. So to the extent that we're aware of these differences in bioavailability between the route in which this critical endpoint, this critical study was derived from, and the inhalation route or dermal, I guess if we're talking about surface limits now, then we obviously need to take that into consideration. And so the data, that are available can vary, but here's a case, and this was actually from a study that a postdoc did for us when I was first starting out at Merck, where the intravenous, that was Trish Wiedemann's work, intravenous and intratracheal instillation resulted in a time course that was very similar, whereas intranasal and oral were very close. And you can see the big differences nominally in how much each of those contributed to the plasma concentration. So to the extent that a particle, for example, is greater than 10 microns, it's going to deposit in the upper respiratory tract. The question is how much is absorbed there before it's swallowed, versus a very fine particle that may get further down into the lungs and have much more residence time and have a higher percentage perhaps. In the absence of data, we assume 100% absorption from the lungs. So there's some conservatism built into our process. So here's a simple example of the OEL setting process. I'll just pick a run-of-the-mill antihistamine, the sedating variety. I know we have some non-sedating choices these days, but the main thing is it induces drowsiness, which is obviously something we want to avoid in the workplace with our workers. Maybe, there were some rare allergic reactions, but those are hard to interpret, and especially if they're extremely rare, setting OELs. This particular compound actually had a 2-year bioassay at the National Toxicology Program, and produced equivocal results, which means they couldn't conclude that it was a carcinogen, even though they saw something going on. And the minimum therapeutic dose, which we would consider a low L because it does produce adverse effects like drowsiness, was 30 milligrams. We knew that the half-life was 3 hours, so it was being metabolized fairly rapidly and not accumulating, so we didn't have to worry about that. So here's the same information. The low L is 30. We used a default uncertainty factor or adjustment factor of 10 for human inter-individual variability. We used a factor of 3 to extrapolate from that low L to a no L. So the composite adjustment factor was 30, 10 cubic meters, and we had data showing that we didn't have to adjust for accumulation, and we knew that the bioavailability, which I didn't mention, was high. So in this case, the OEL is 0.1 milligrams per cubic meter, and that's at the low end of OEB2 for those that like OEBs, occupational exposure bands. The type of OELs and types of OELs and TLVs is expanding. I should have probably put TLV surface limit at the bottom of the slide. And next time I do a talk like this, I probably will. But we have 8-hour time weighted averages. Trying to move. I'm hoping that you're not seeing this. Okay, my picture is covering up part of the slide, to which nearly all workers, which is kind of a key point. If you think about it, and that's never been defined. Is it greater than 95%? What is that number? But that's part of the definition. Can work with a day after day for a working lifetime. So that's an 8-hour number, averaged over 8 hours. We have short-term exposure limits are reserved for compounds that can produce immediate effects. They can influence a worker's ability to actually escape if they needed to. It's kind of like ERPGs, if you're familiar with those, emergency response planning guidelines. But these are 15-minute numbers, typically, spaced at least an hour apart, no more than 4 in a given day, while still maintaining, or complying with the TLV TWA, the 8-hour number. I think Doug mentioned the ceiling earlier too, that is a concentration that should not be exceeded at any part of the workday. And that one is reserved for things like hydrogen fluoride or things that are just so nasty and produce immediate effects that need to be dealt with. So we want to limit the peak exposures with those. So how are the OELs used to identify and mitigate occupational health risks? We're going around clockwise here. Now we're getting into the exposure assessment side and trying to understand what the risks are. Presumably the results are coming in less than the OEL and good. And this is before we even get to, okay, where are we and what do we need to do about it if we need to make a change? So I thought I would include a few slides here to just kind of show how we used to think about it when we had air monitoring data. We used to do occupational health risk assessments to help the hygienists understand what the risks were or what health effects might be expected if there was an overexposure. So already, the compound, had an exposure limit, and they can be used within a banding scheme also, because you can go right from the exposure limit to the controls. But this is a figure that came from a paper that we published some time ago about, we called them performance-based exposure limits before control banding was used. And the idea was, I think at Merck they started setting exposure limits. They called them exposure control limits at the time, back in the late 70s. So with about 10 years of experience, they realized what sorts of engineering controls needed to be used to meet those limits. And then so we had Mevacor, and then anti-cholesterol drug, for example. I think it was 50 micrograms per cubic meter. They knew what they had to do to control that, and then simvastatin came around. So Zocor, and so okay, we know, what sorts of engineering controls are needed to control to that level. And so, if you have a system like this, then it's fairly easy to drop, new compounds in, and it shows the correspondence between the bands. And notice that OEB 4 and 5 here, we're less than a microgram per cubic meter, at least in the pharmaceutical industry. And in the systems that David was talking about kind of stop at about 10 micrograms per cubic meter. So, yes, you're seeking expert advice when you're going below here. But it just shows that in some industries, and I'm sure there are industries out there that have compounds. We certainly have TLVs that are down in this, down in this range too. So I guess hopefully that, and it does look like it's, it's being genericized and could be expanded to the concept is good, to any industry. And so what happens is they get banded, the engineering controls are recommended, the facilities are built out, and then we have to go and verify that, that we're actually meeting the limit that we intended. So the design target, when basically is when the industrial hygienist goes out and does the monitoring after it's installed, we want to see it, the vast majority of samples coming in below the OEL. So depending on the process variability, you could have a geometric standard deviation that ranges, I've got 1.5 to 3 here, just to show roughly, what kind of data you might be hoping to see. And so the OEL is really a key factor, determinant in facility design. Okay, so we're running along, and maybe there's some upset conditions, or maybe we haven't gotten to certain processes or whatever. And so, I wanted to include this slide to kind of to illustrate the thinking process. So, up on the top here, we have below the OEL, so we're in compliance. You look at OSHA's, compliance strategy. It's either, significantly below, you're compliant, it's indeterminate, like on that red line, or, you're definitely above based on the 3 samples or whatever that are taken. And so we're looking at the incidence of adverse health effects here. And on the bottom, we got the OEL, and then we have the low L. So the difference between those is the safety factor, right? The composite adjustment factor. So what we're trying to communicate here is that, and we know that health effects in workers are influenced by any number of things other than exposure, and maybe they're more susceptible, maybe, there are some mixtures, other interactions going on. But as you start moving from the left to the right, below the OEL, you wouldn't expect to see any adverse effects. That's the goal, right? So, and then as you move right, I'm not saying that you would definitely see health effects when you're above the OEL. The OEL's 1, and at 1.1, it's still highly unlikely that you're going to see any health effects. And as you move up toward, the critical end, the point of departure that was used, the low L, now, the likelihood of adverse health effects is going up. So you could say, well, it's possible. And if you're above the low L, where you actually saw effects in animals or maybe humans studies, then it's pretty easy to say that, if you're above that level, then it's quite probable that you would expect to see adverse health effects. So we came up with a simplified version to include in the slide deck when the industrial hygienist was communicating the results to the employees, which is a requirement. So, so this is designed to help put the potential health effects into perspective. So same logic here, it's just on a sliding scale, and so where you position the arrow is kind of key. So fortunately, in most cases, when the monitoring results come in, they're like wondering, well, you were here, what were the results? What does it mean? Am I going to have any health effects? And so this was a useful way to communicate to the employees. In this case, their exposure with respiratory protection. So I guess in this case, they were relying on the protection factor of the respirator to say none expected. Now, without, depending on the protection factor, you're off to the right somewhere, right? Depending on what respirator you're using. So we just found this to be a useful way to help. And it helps you understand too where you are relative to the risks. So this is all about going from the hazard piece and the dose response and out. Okay, now we're factoring in exposure. Yes, we can do a risk characterization. And the mitigation steps are obviously going to be commensurate with the risk. So it's important and probably equally important for communicating to management about the need perhaps to improve engineering controls, for example. All right, so let's move on to notations. I mentioned skin, has been around forever. DSEN, RSEN, dermal respiratory sensitizer, and the new one, ototoxicant. And the idea of notations is to highlight a special hazard that's over and above, what you need to know to control the, exposures. It's not just the OEL or the TLV. There may be something unique about it that would cause you to do something different. So, for example, with dermal sensitizer, maybe we're talking about adding extra protective equipment, sleevelets or gloves, whatever. So the idea is to really highlight the situation. It's kind of like labeling with the hazard statements. It's making people aware of a particular hazard, but these are designed to supplement the TLV or the OEL in a way that causes something else to happen, put it that way. So skin notations are typically used to highlight the potential for a significant contribution to the overall exposure by the cutaneous route. So you might be meeting the OEL, but if it's zipping through the skin, then you're getting more of a dose that way. And this does include, exposure to vapor, through the eyes to vapors, etc., as well as direct contact. And obviously, it also is important to highlight or reflect the fact that we may have had dermal studies in humans or in animals that actually show that absorption is happening and can cause systemic effects. It's not enough just to show that it gets in. It has to actually produce an effect in a study or be likely to produce an effect based on other studies where we had the kinetic data to show that if you got this much of an exposure at these blood levels, you would expect this effect. So there's actually a lot that goes into setting a skin notation. We don't do it lightly, but I think there are about 100 TLVs that have skin notations. In fact, we're using that as a way to prioritize the setting of surface limits right now, along with some other considerations. So DSEN and RSEN notations, they were originally combined for many years under the SEN notation. It included both. But, we thought that separating them actually helped with the goal, which was to try to steer the hygienist toward, what sorts of controls would be appropriate. And so with a dermal sensitizer, maybe, what you do is a little different than if you had a respiratory sensitizer in terms of engineering controls or administrative controls, PPE, et cetera. But in both cases, these are designed to highlight that hazard or those hazards and to prevent future cases of dermal and respiratory sensitization. I'm going to give you an example at the end of how we would set a surface limit for a skin sensitizer. And again, the idea is to prevent new cases because once you're sensitized, then it's a lot more difficult to prevent those. We're just trying to prevent the induction of sensitization. And there are different types of sensitizers. And they have different mechanisms of action. Dermal sensitization is type 4, or delayed hypersensitivity, involves T cells. And the respiratory sensitization involves IgE, and that's more of a type 1 immediate. But with dermal, it's mostly dermal. It's manifested as a rash, and with respiratory sensitization, you can be sensitized dermally, and then exhibit, bronchoconstriction or some of the other symptoms that you see here. So, with the descent notation, we look at human data and animal data. With animal data, we have a lot of old data from the guinea pig maximization test, which has been supplanted and replaced by the murine, the mouse local lymph node assay. And we're looking at, with human data, number of case reports. And just like with the H statement, it's got to have a significant response rate in order to trigger that. And so we look at all the data. If you just have one case report, it might not be enough to assign based on human data. The local lymph node has been assay, as I'll discuss in a minute, is really useful because it provides a dose response for the induction of sensitization, which is really what we're trying to prevent. And then, more recent studies have looked at cytokine levels, and there's analogy that you can use. So here's an example of something that clearly deserves a descent notation, paraphenyldiamine, and one that doesn't, picric acid. And so we had, the phenyldiamine was a potent skin sensitizer in guinea pigs at very low concentrations, many, up to 100% responding. We had human data. So the data were very clear for that comment. Whereas picric acid, yes, there were a few reports, but it wasn't clear what was going on. And it might even have been just irritation that was doing it. So the data, although there were some data, it wasn't sufficient to assign a descent notation in that case for picric acid. Arsine notation, same thing. We look at animal data, we look at human data. Whether animal data is tough because there are no validated tests for respiratory hypersensitivity like we have with dermal sensitization. In humans, we're looking at allergic antibody, IgE, pulmonary function testing, et cetera. And so, those are the criteria off to the right here, similar in terms of number of responders, the severity of the response, and so forth, and proof that they actually developed an allergy or will respond, with pulmonary function testing in a way. So TDI is a classic example of a respiratory sensitizer with lots of data to support that, both animal and human, whereas Terrell, there were concerns about it early on, but the data were insufficient in this case to assign arsine and some of the nosebleeds, coughing, et cetera, was probably more of an irritant response rather than a sensitization response. We had no animal data in this case. So what happens when you see a descent or arsine notation? Well, it's part of it is increasing awareness, and that goes a long way actually in preventing future responses. So the notations are assigned, OEBs are assigned, safety data sheets are updated, labels are made, and training programs are provided. And then, in terms of design, what I'll show in a minute is that, for strong sensitizers, additional engineering controls and PPE are probably needed. For weak to moderate sensitizers, you have to make a judgment as to whether you have to go that far, and the surface limit is designed to help there. And just reinforcing good chemical handling practices might be sufficient. So if we have either of these, we want to set surface limits if we can, if the data are available to allow you to do that. The ODO notation highlights the potential for chemical to cause hearing impairment. And so even if noise levels are below 85 dB, it's reserved for chemicals that have been shown through animal studies, human studies to cause a permanent threshold shift at specific frequencies. And again, the idea is to focus attention not only on engineering controls, but maybe the possibility of implementing hearing loss program. And so it's not a requirement, but it's something to be considered, especially even if noise levels are below that are compliant. So hearing conservation, medical surveillance, so those are the sorts of things that are, we hope people will think about. Styrene is a poster child for auto notation, and TLV was recently updated with, in the STEL to include an auto notation. And so, there were plenty of human data in this case. It was a difficult data set to review because you wonder how much of the hearing loss resulted from prior exposures, because it's permanent. And so the more recent studies did show that it's possible, and in the range of 20 to 40. So there's not a huge safety factor there, but and this is assuming that peak exposures are managed properly, which can certainly contribute to hearing loss. So again, same thing. When you see the auto notation, there are a number of things that hopefully industrial hygienists will think about, including, enrollment in hearing protection program, which may be appropriate, and perhaps updating engineering controls. So moving on to the last part of the talk, surface limits. So I want to just go through some basic concepts here. So surface limits are something that has not been the focus, up until now. There are some exceptions, but dermal exposure is really associated with a good number of work-related illnesses. And we've used skin and sensitizer notations, but we felt that it was time that we start setting surface limits for certain compounds. So, a lot of organizations that are listed here, have made good use of the notations. And really, in the U.S., lead and chromium have surface limit or certain wipe sampling requirements. The DOE has a number for beryllium, And EPA, as part of the registration process, requires some sampling for pesticides. So you can probably count them on one hand, right? So the surface limit, just like the OEL, it's a concentration on workplace equipment and facility surfaces that's not likely to result in adverse effects. Same concept, following direct or indirect contact. And it's really intended to supplement the airborne limit, especially for compounds that can go through the skin, so skin notation or the descent arsen. And I mentioned A1 and A2 carcinogens because, the footnote in Appendix A in the TLV book speaks to the need to control exposures by all routes for A1 and A2 carcinogens. So they're intended to protect against systemic toxicity, sensitization, and cancer, from that perspective. And we're just getting started. We've only set limits for a handful of compounds here. I'm going to use one or two of these as examples to illustrate how that can be done. So, it's a real issue. The processes are not totally closed, typically. So you do get surface contamination. It's important to keep in mind that visual limits for contaminated surfaces range from 100 to 500 micrograms per 100 square centimeters. So that it's good to keep that in mind because especially for compounds that are very potent or toxic, they may still be, they may be around on surfaces at levels below what can be seen. So they may still represent a risk. So that's why, especially for those, it's important to think about surface limits if we can set them. So, there are issues around that are obvious, and we still have to work through in terms of, direct contact, how much is transferred to the skin. And we know that the amount that's absorbed through the skin is determined by a number of factors, physical chemical properties and other exposure-related factors. But fundamentally, setting a surface limit starts with the dose, just like setting OELs or TLVs. So if we have a dermal study, that would be very useful. If we don't have a study, then perhaps we can extrapolate from that the dose that was received at the TLV, if you assume you're exposed for 8 hours and breathing in 10 cubic meters. So the occupational ADE, that the starting point would be the TWA times 10 cubic meters. And then you can just divide that by 100 square centimeters and you have your surface limit. Of course, adjustments, do need to be made to correct for differences in bioavailability, depending on what the point of departure was for the TLV, if it was an oral study, for example, or inhalation, and all of the different routes have to be looked at and adjusted in a way that makes sense. And Tracy Kimmel wrote a paper describing this. I included that one and a few others in a list of references at the end. So there are a number of uncertainties and limitations, as you're probably all thinking about right now, about how this is going to work out. What is the exposure scenario? How many, what are the number of contacts per day? What's the total surface area contacted? How do I relate this, milligrams or micrograms per 100 square centimeters to my workplace? How complete is the, absorption? When I go out to do the wipe sampling, what's the recovery? So all of this needs to be taken into consideration. Is the skin healthy? Is it damaged? You could have a higher absorption rate. So just philosophically, as we're going through this, we're, wondering how much of this should be done on the limit setting end, with adjustment factors, and how much should be addressed by the exposure evaluation and the risk assessment. In either case, you need to know what the assumptions were going into setting the limit. So we're trying to be careful as we're summarizing these, and we're using a few extra words to explain exactly how it was derived, and so that you can then extrapolate it back to your situation. So the basic calculation is the same. It's very similar. This time, we got the ADE, occupational ADE, divided by 100 square centimeters, and we're adjusting for bioavailability. It's pretty straightforward. Got a couple examples. Ethylene glycol dinitrate. This time, we only had a STEL, so we extrapolated from the STEL. It does have a skin notation. It calculated a surface limit of 20 micrograms per 100 square centimeters. The TLV basis for this compound lists headache, hypotension, some cardiovascular changes. So what I did here, what we did was we calculated the dose that would be received in 15 minutes at the STEL. Okay, so that was 0.0622 milligrams per cubic meter. That's well, no, that's the STEL. So over 15 minutes, you get a total of 0.019 milligrams. I rounded that to 0.02. So you go through and do the arithmetic, you end up with a dose of 0.02 milligrams, and dividing this by 100 gives you which is the surface area of the palm of one hand, and also the standard surface area for doing wipe sampling of 0.02 milligrams per 100 square centimeters. And this is the same calculation just shown with the equation here. So just milligrams per cubic meter times cubic meters to get milligrams. And then in this case, we assumed 100% absorption to the skin and through the lungs. And we end up with 20 micrograms per square centimeter, 100 square centimeters. Next one is phenylethyl alcohol. And it looked like we should be considering a surface limit here because we had a skin notation, it was producing embryo fetal damage. But when we went through, we realized that the data on the kinetics were somewhat inconsistent, where at least a very limited human data showed that the absorption was relatively low compared to the rat skin. So 7.6% versus rat skin 77%, and rabbit was a little lower. But when we looked at the study, we realized that in the human study didn't involve occlusion. So there was a lot of absorption. I mean, a lot of evaporation that occurred. So it probably underestimated the amount that was absorbed through the skin. So, but in the meantime, we know that PEA produced developmental toxicity in rats at low dermal doses, 70 milligrams per kilogram. So we had a dermal study in rats. And so we did the calculation, and the 70 milligrams per kilogram times 70 kilograms in this case, could have used 50. Overall conclusion is the same. So just 49 milligrams divided by 150. Now that 150 is the composite uncertainty or adjustment factor, and the 1.3 is the bioavailability correction factor. So that's 1% divided by 100% divided by 77, it should be 100, 1.3. And the human absorption, if we use that lower value, 7.6, and an alpha of 0.1, see in the denominator here, that increases the number by a factor of 10, right, by doing that. So with the first number, it would have been about 1 here, it would have been 25. But if we actually use the human data, 250 milligrams per 100, well, that's a heck of a lot higher than 100 to 500 micrograms per, that would be visible. And it's not consistent with good industrial hygiene practices to have that much on surfaces. So considering the high level, well above visual thresholds, and the fact that it has a high vapor pressure, I mean, even if you wanted to do wipe sampling, it would probably be gone before you got there. It was decided not to recommend a TLV surface limit for phenylethyl alcohol. So it doesn't happen all the time, but we, where it looks like maybe we go through the motions and try to calculate one. Now, the third case, the last one, is setting a surface limit for a skin sensitizer. And we know, that's a major concern for workers. I mentioned that the local lymph node assay is used to identify skin sensitizers these days. And you can calculate a surface limit using the EC3 value, and I'll explain what that is in the next slide. So we know that there's a good correlation between the results that we get in the local lymph node assay and human repeat insult patch testing. And that informed the choice of adjustment factors for, for interspecies extrapolation. And then from a risk assessment, risk management perspective, we just want to know how to maintain, safe levels in the workplace for skin sensitizers. So, how low do we need to go to prevent future cases of sensitization? So it designed to feed right into the overall comprehensive exposure control program. So as I mentioned before, there's different types of different mechanisms going on, whether it's dermal or respiratory hypersensitivity. But you can pick up both of those in a local lymph node assay. There's different cytokines involved. But on the left side, the induction phase or the sensitization phase, the chemical comes in, interacts with cells that go into a lymph node, they proliferate, and then they go up to the right and are in the skin waiting for the next challenge from the chemical. So the challenge phase in these studies, follows the induction phase. So the elicitation is on the second exposure, and it may take several weeks for a worker to develop an allergy. Sometimes it takes years. We have laboratory animal allergy as an issue in the pharmaceutical industry, and some workers animal handlers can work there for decades without having symptoms, and then one day, have a problem. So it's individual. People have different susceptibilities. Anyway, in this case, now we have all the other cells involved, and it triggers the allergic reaction that you think of: swelling, bumps, rash, and there's other cells, mast cells, et cetera, that are involved. Anyway, this is really the illustrates what we're trying to do. We have on the left-hand side stimulation index. So this is where on the induction side, the lymphocytes are proliferating, and they use there's a radioactive method, there's a non-radioactive method. But bottom line is you put the chemical on the ears of the mice, and then you take out the lymph node the lymph nodes in their neck, the auricular lymph nodes, and you measure the amount of radioactivity. And here with dinitrochlorobenzene, which is actually the positive control in the guinea pig maximization test, you can see there's a very good dose response. So toxicologists like to see this sort of a curve. And so the EC3 is the effective concentration that corresponds to a threefold increase in lymphocyte proliferation above controls. Okay, so that, that's the test and how we interpret it. And that's like a NOEL, right? Or NOEL/low L. It's kind of like a benchmark dose in a way. And so then, how do you then convert that into a surface limit? So you have to think about, how much do these mice behave like people? And you can see with these well-known sensitizers here that Gerber, published, you can see there's a good correlation in terms of the potency for these. So the ones at the top are the most potent sensitizers, strong, moderate, weak, going down. And so you look at this ratio, and they bounce around a little bit, but the highest number is 6.5, which is why we recommended, I published a paper with Susan Arnold from the University of Minnesota a couple of years ago on this, and we went through the literature and looked at how risk assessments are done for sensitizers, mostly in the cosmetics industry, et cetera, and flavorings. And so we came up with a default adjustment factor recommendation of 50. So you would take the dose that was equivalent to the EC3 and divide it by 50. So we got 6 reflecting that ratio, the variability in that ratio. There are matrix considerations, that typically when things are tested they're mixed in a certain solvent. They're trying to maximize absorption in the workplace. It's probably neat material. Maybe it's in solution. With the animal studies or the human studies, it's just 1 or 2 exposures in the workplace. It could be more of a chronic situation. And then, you might want to do, additional adjustments based on the potency of the sensitizer. It may be a little double dipping if you consider, you're already starting with the EC3. But the calculation is very straightforward. You start out with the concentration of 0.051 for orthophthalaldehyde in this case. You go through and do the calculation. It's 25 microliters are applied to the ear, which is about 1 square centimeter. So the EC3 for orthophthalaldehyde was 13 micrograms per square centimeter. So to derive the surface limit, we take that and divide it by our adjustment factor, which is 50, and then multiply it by 100 to normalize it to 100 square centimeters. So in this case, it calculated out to be 25 micrograms per 100 square centimeters, and that's well below visible. This is used as a sterilant for surgical equipment. You start out with the EC3 values here, and they range from 0.01 down to 40. So potent sensitizers down to weak sensitizers. And this particular one ended up between 10 and 50. So, it would be, considered a pretty strong sensitizer. But if you go a little bit further down, right, down you're, quite a bit below the surface, the visual limit, right? And so, armed with this information, you can say, okay, my compound is 25 micrograms per square centimeter. How does that line up with the overall, like the level of control that would be required to achieve that level based on past experience? And you can see here, we're talking about now kind of OEB4 range, right? So, and the corresponding occupational exposure limit, for that would be in the 1 to 10, microgram per cubic meter range. So 25 micrograms per 100 square centimeters is, it's a pretty low number. We're going to have to make sure that we're cleaning up after ourselves, et cetera, or there may be some extra procedures involved after the process is completed. And that's, again, it's really just like the notations. It's really designed to highlight the hazard and to provide some useful information to help control exposures to the appropriate level. And so it also surface limits, at least in the pharmaceutical industry, were used for a number of other purposes, like decommissioning areas, or after a bay was cleaned up, when is it okay to hand it over and allow the next product to go through. So, it's good for sensitizers, good for things that are toxic dermally, and it's something that, unfortunately, and I don't know why this has been, we really haven't taken advantage of it for many years. So we're just trying to introduce it now, and we're hoping that people will start making use of the surface limits and give us some good feedback about how it worked, and maybe we would perhaps modify even how we're setting them. But it's a team effort. It's not only setting the limits, but how they're used, how useful are they for your purposes. So I just wanted to the last two slides supplement. The surface limits are obviously designed to provide some quantitative criteria that go above the kind of qualitative notations that that we've done in the past, and it's part of an overall program, and the importance of really understanding what the basis of the surface limit was, just like with the OELs, and trying to communicate and understand what the rationale was so that you can apply it in the proper way. And again, it comes back to really understanding the assumptions that go into setting the limit and your particular exposure evaluation. So hopefully I've given you some, good background on how we set OELs, how we set surface limits also, and how we leverage notations and surface limits to really put perspective on risks and to help you understand where you are and how much work needs to be done to control exposures to safe levels. So with that, I'll stop. These are the references that I mentioned, and be happy to take any questions.
So we have one question from Doug to you, Bruce. It's where does the 10 cubic meter of air breathed in an 8-hour day come from?
Well, that was, I can't remember the reference, but it was an old reference that has survived the test of time. It's basically someone did the measurements of breathing rates, and it's actually, I think the definition includes while engaged in light work. And so EPA has the Exposure Factors Handbook has a lot of information on this too. So there are different numbers out there, but the rule of thumb has typically been just 10. And when you think about the variability in the process, sampling and analytical error, plus or minus, and these are not bright lines anyway. So, but that's pretty close to what you would expect in the workplace based on earlier studies.
And he has a second one. Do you have a favorite toxicology book that you recommend industrial hygienists have in their library?
Casseret and Duel is the classic, and I think there's a simplified version of it it's like a soft cover, and I would look for that. I don't have it, but I've seen it. You could Google it too. I don't know. Probably there's lots of good information out there. And attend one of the seminars that we're going to have in this fall. We'll get into a little bit more detail on some of this. Webinars.
Well, if there are no more questions, that concludes our seminar for today. Our evaluations and certificate of attendance will be sent to all our attendees by email. So if there's no questions, we'd like to thank every single one of you for joining us today, and we would love to give a million thanks to our speakers and to Jan Cohn as well for helping us put this all together.
Can I throw out something for a minute?
Of course.
Yeah, we don't know about the next speaker series, IH speaker series like this. I mean, I'm doing this on behalf of Gulf Coast AIHA in order to keep the CE thing going. We already have the PDC. We're doing a joint PDC with ASSP on April the 21st. Hopefully y'all have already seen some initial stuff going out. We finally got the agenda played out. So usually we do this every other month, but with conference coming up and with that PDC in April, I guess I'm looking for some feedback and or speakers and or topics, if anyone's tuned into to try to get another one together. If anybody has any burning feedback on where, when, and what kind of topic we could look at, or you want to wait till after conference. I don't know if people are going to conference or if we want to wait till the summer and do it in June, as opposed to, I don't want to do it in April because I don't want to compete with the PDC that we're doing on Friday the 24th. And I don't know if we could squeeze one in earlier in May before conference, unless everybody's going to conference. So any feedback with me, please share, email or personally or whatever works.
Here at the Southwest Center, we were talking about sending a survey out to our regular attendees and just asking them how often they would like it, any topics they would like to see covered, whether they like it online, whether they prefer a person or a hybrid. So we were brainstorming about gathering that information from our attendees.
Super. Well, let's just do it that way then. But yeah, if anyone has any specific feedback, please holler at me. And Sylvia and Serena, absolutely great. Thanks for corralling us and making us put it together. And we should have done the agenda a little earlier, but we definitely do want to get the word out and let people know that we're doing these kind of CE things to help people with CM points, as well as get the latest and the greatest. These presentations were great. I thank my speakers tremendously. And you'll relay about the how to get CM or the CE documentation stuff?
Yes.
Okay. Excellent. Thanks, guys.
You're welcome. Thanks.